What if planets are not the largest worlds a civilization could inhabit, but among the smallest? What if Earth-sized worlds are only the beginning, and the homes of the distant future might be cubes, disks, hollow spheres, oceans without shores, rings wrapped around stars, or artificial planets containing the living area of 1,000,000 Earths? The universe gives us planets. Engineering lets us choose worlds. The dream of settling space usually begins with finding another Earth, Mars, Venus, Titan, or some distant planet beneath another sun. Yet once a civilization learns to build on astronomical scales, finding the right world may matter less than deciding what kind of world it wants to create. Even if the galaxy offers billions upon billions of planets, nature does not build them to our specifications. We could terraform some to better suit humanity, or bioform humanity to better suit them. But either approach begins with whatever nature happened to provide: its gravity, atmosphere, geography, day length, climate, resources, and location. Artificial worlds let us begin with the gravity, climate, and geography we want, then build outward from those choices. Day and night become design choices, so do seasons, oceans, horizons, weather, and even the direction of down. We can build worlds far more spacious than natural planets, or ones small enough to bicycle around before lunch. We can place them around stars, between the stars, or around black holes. We can give them landscapes nature rarely creates, and some it never creates at all. Earlier this year, we released our first major space habitats compendium, examining structures most likely to become the ordinary homes of a spacefaring civilization. Oneocylinders, Stanford tori, Byrne spheres, linked habitat clusters, and other rotating worlds that can be constructed incrementally and repeated by the millions. Those are probably where most people living in space would actually reside. They are efficient, modular, and comparatively practical. They can begin as towns or industrial settlements, expand alongside their populations, and eventually form immense artificial archipelagos of cities, farms, industries, and ecosystems. Today, we are leaving comparatively practical behind. This second compendium explores the most extreme habitats we could construct without abandoning known physics. Some solve genuine engineering problems. Others trade simplicity and efficiency for vast, continuous landscapes, beauty, novelty, privacy, prestige, or sheer spectacle. And some belong to a category I call because we can megastructures. Things a civilization builds partly because the universe neglected to include one, and somebody decided that it should. We will begin with artificial planets small enough to walk around in a day, including worlds shaped into cubes and other polyhedra. From there, we will move through enclosed worlds, spinning cities, floating settlements, bubbles of atmosphere larger than stars, hollow planets containing stacked landscapes, artificial suns, weightless ecosystems, and oceans built where no planet ever existed. Then the scale rises through flat Earths, Sombrero Planets, hoop worlds, Ringworlds, and disks extending across entire solar systems. Finally, we will build planets around black holes. First, mega-Earths offering around 1,000,000 times Earth's living area, and then Birch Planets so vast that an entire galactic civilization might inhabit one without ever developing faster than light travel. None of these structures is necessarily the cheapest solution. A swarm of ordinary rotating habitats would usually be easier to construct than one continuous world wrapped around a star. A sphere is easier to hold together than a cube, and nature has very good reasons for preferring the one over the other. But civilizations do not build solely for maximum efficiency. We already devote resources to monuments, parks, cathedrals, museums, resorts, record-breaking projects, beauty, and spectacle. We preserve landscapes that could be converted into more productive uses and undertake difficult projects simply because the challenge matters to us. A civilization commanding the resources of an entire solar system would presumably do the same on a solar system scale. Nor does extravagance necessarily mean uselessness. An artificial planet might also serve as a reservoir for hydrogen and helium. A giant shell might combine habitation, radiation, shielding, power collection, industry, transportation, and long-term material storage. The practical infrastructure and the because we can megastructure might often be the same object. The extravagance lies in deciding that a necessary fuel depot should also have continents, oceans, forests, and a sky. One production note before we begin. This compendium draws from episodes recorded across roughly a decade of the channel. My speech impediment, now essentially gone, is much more pronounced in some of the older material, including recordings made after I had already begun speech therapy. We've replaced some sections with new recordings where it interfered too much, while preserving others whose ideas and presentation remained worth including. As a result, my voice, the graphics, and the production style will change as we travel through the episode. You do not need to have watched the first Space Compendium either, though together the two episodes form a broad tour of the artificial worlds humanity might someday call home. As we go, do not ask only whether each design could be built, ask which one you would choose. Would you prefer a private microplanet whose entire horizon fit within a day's journey, a continent beneath an engineered sun, a city floating in an atmosphere thousands of kilometers deep, a continuous world encircling a star, or a planet so enormous that no resident could explore more than a microscopic fraction of it in its lifetime? This will be a long journey, so grab yourself a drink and a snack. Before we build the strangest homes imaginable, however, we need to understand the rules governing them, how habitats create gravity, why larger ones feel more natural, and why increasing scale eventually force us beyond ordinary construction. Let us begin with the basics of habitat scaling. Basics of habitat scaling. When we talk about space habitats, we need to draw a line between a space station and a habitat. A station, like the ISS, is a machine, cramped, dependent on constant resupply, with life support more fragile than comfortable. A habitat, by contrast, is a home. It provides air, water, farmland, and gravity. Not just survival, but the comforts and scale of civilization. This does not necessarily have to be large or stationary. Nothing in space really is anyway, but we tend to assume many interplanetary ships, and certainly most interstellar ships, would have habitats aboard designed for long durations. Thus, while a habitat does not need to be a completely enclosed and self-sufficient ecosystem, we tend to assume they are either fairly self-sufficient or part of a wider conglomeration of habitats that are in total, much as a city and a farming community are not really complete without each other for trade. One could use a wider definition of habitat to mean many interconnected space stations, and we will look at some variations on that today too, but we try to limit habitat to a single large structure or directly connected sections a person could walk, swim, or fly to, and use terms like communities, conglomeration, clusters, or nations for the other. Now, to go from a structure to a habitat specifically, and excluding microgravity habitats that again we discussed recently, our first challenge is gravity. Without it, humans suffer bone and muscle loss, fluid shifts, and other health issues. Moreover, you are not going to have a realistic simulacrum of a terrestrial ecosystem without relatively normal gravity. Engineering an ecosystem based on low or no gravity might be an awesome task, a great challenge that might produce great wonders, and yet it won't be Earth-like. Now, planets provide gravity for free, but often not what we want or where we want it. But in space, we usually turn to rotation, or what we call spin gravity. Spin a cylinder, ring, or torus fast enough, and centrifugal force gives you a down direction. The larger the radius, the less spin you need, and the more natural it feels underfoot. People often wonder how we know this works, and we know it from every time we use a washing machine, which spins water out of your clothes by making the internal gravity higher to drip it down to the sides of the drum. Down in such environments points out, and up to the center, and you live inside on the interior of the drum. People often wonder how gravity works in space, so let's clear up a common misconception. The International Space Station, and everything else in orbit, does not actually escape Earth's gravity. In fact, at the altitude of the ISS, gravity is only a few percent weaker than here on the ground. Astronauts float not because gravity has vanished, but because they are in free fall, circling Earth sideways fast enough that their fall around the planet matches the curve of the surface. The result is weightlessness, or more precisely microgravity. Now, what about inside a spinning habitat? If you jump off the floor, will you suddenly float? No. Just like touching the wall of the ISS does not change the pull you feel, jumping inside a spinning drum does not cancel your gravity. The centrifugal force from rotation keeps pressing you toward the hull. But is spin gravity identical to real gravity? Not quite. In a rotating frame, the pull gets stronger the farther you are from the center. Double the distance, double the force. Real gravity follows the inverse square law, double the distance and the pull drops to a quarter. That means in both environments your feet feel a stronger pull than your head, but in a spin habitat you need a structure at least 10 times taller than a person before that difference stops feeling strange. Larger habitats solve this by spinning more slowly to reach the same gravity, which also helps to avoid nausea. Like rotating planets, spin environments also come with some Coriolis effects, but they manifest differently. Try moving radially, inward or outward, and you find yourself deflected sideways. It's subtle in large cylinders, but obvious in smaller, faster spinning habitats. So when it comes to spin habitats, bigger really is better if the goal is to make the environment feel Earth-like. We generally prefer a rotation rate of 2 RPM or slower, and ideally close to 1 RPM or less. That's 1 full spin per minute or even slower. And this is not going to make you feel sick or nauseous any more than turning around in your chair over the course of 1 minute would. At 2 RPM, you can generate 1 Earth gravity with a radius of about 224 meters or 733 feet. That is already a large structure, but dropping the spin to 1 RPM is even nicer for comfort. The catch is that at half the rotation rate, the required radius goes up with the square of the change. You need a habitat 4 times wider to get the same 1G. Keep that in mind for later, because in theory, the most natural habitat of all would be one so large it only rotated once per day, like Earth itself. A quick side note, while the spin rate in RPM gets slower as the habitat gets larger, the tangential velocity at the rim actually climbs sharply. It scales linearly. Double the radius and you double the rim's speed. The kinetic energy to spin it up grows even faster, with the square of that speed. In other words, a habitat twice as wide takes 4 times the energy to get rolling. Fortunately, space is a frictionless environment, so once set spinning, a habitat will keep turning for ages with only occasional boosts to make up for long-term losses. This is where we get our first 2 well-known structures, the von Braun wheel and its larger successor design, the Stanford Torus. The von Braun wheel itself is not what I normally call a habitat, merely a space station, at 125 feet in radius and only designed to produce weaker gravity akin to Mars, which is 38% of Earth's. The Stanford Torus is a design from a couple decades later when we were thinking about people living in space, not merely being stationed there for a while. It's over a mile wide, 1.1 mile in diameter or a radius of half that, 894 meters, and that is the 1 RPM radius for normal gravity, so it's not an arbitrary design size. Bigger places cost more, but your raw materials for things like air, water, and soil for on the inside scale linearly with living area, so you can't just build bigger if you want to. Double the living area, double the budget for mass. And moving to design like the modified Byrne sphere, the original and much older design was actually a non-rotating microgravity habitat, or the O'Neill cylinder, which has a diameter of 5 miles or 8 kilometers, and is a long can or cylinder design, and comparable in size to the typical American county, of which we have about 3,000. So why can't we just scale habitats up endlessly? Well, physics sets limits. All that mass under spin is straining, and very akin to a suspension bridge, the same length as the circumference of that habitat. The materials begin to tear under their own weight. For a ring or cylinder habitats, tensile strength is the defining factor. For other designs like giant domes and shell worlds, which we'll get to later, it's compression and buckling under its own mass and gravity. The O'Neill cylinder is designed for using steel as your building material, and with lots of leeway for extra mass or damage. We could go bigger with modern steel and more with aluminum, or other even stronger tensile strength materials like Kevlar or graphene. We have some tricks for circumventing even these limits, but we'll get to them later too. Fundamentally, space gives us freedom to build bigger than any planet, but it also makes us answer to geometry, mass, and the stubborn rules of mechanics. Because we can. Those physical limits tell us what kind of habitats we can build. They do not tell us which ones people will choose to build. Most future habitats will probably follow a handful of efficient, reliable designs. Once a civilization has learned to mass-produce rotating cylinders, rings, and enclosed settlements, there is little reason to reinvent the structure every time somebody needs more living space. But practical designs will not be the only ones. Human beings already construct monuments, luxury resorts, record-breaking skyscrapers, elaborate gardens, and machines built partly to prove that they can be built. Sometimes the purpose is prestige, tourism, religion, art, or national identity. Sometimes people simply enjoy attempting something difficult. I call the largest examples because we can megastructures, or BWC megastructures. A cube-shaped planet is not more efficient than a sphere. Gravity naturally favors the sphere, while the cube requires extra structural support, unusual mass distribution, and constant maintenance. Yet it would also be instantly recognizable, culturally unique, and probably one of the greatest tourist attractions in the star system. Its impracticality would be part of its appeal, and we have any number of famous bits of architecture to prove that can work, not discarding any functionality, but giving it second place to personality. That does not mean these structures must be useless. A strange artificial planet might also store vast reserves of hydrogen, helium, water, or metals. Its active supports could test engineering later used in ordinary habitats. A project begun as a monument could become a laboratory, industrial center, ecosystem preserve, cultural capital, or all of those at once. Nor do many people need to prefer a design for it to exist. In a civilization containing trillions of habitats, a structure chosen only once in a billion cases would still have thousands of examples. Across the galaxy, even the rarest architectural preferences might appear millions of times. Once basic living space becomes cheap, efficiency may stop being the only consideration. Privacy, beauty, novelty, history, challenge, and the desire to possess something unlike anything else may matter just as much. And extravagance does not always mean building larger. A world small enough to walk around in one day might be every bit as unusual and luxurious as one spanning the entire solar system. So before we climb toward the greatest megastructures imaginable, let's begin at the opposite extreme, and ask how small a planet could become while still feeling like a world. Imagine standing on a world where the horizon isn't a dozen miles away, but just a few hundred feet, where you can see the land curve beneath your feet not as a distant arc, but as something intimate and undeniable. A place where, if you felt ambitious, you could walk all the way around your planet in a single day, or jog the circumference before lunch. It wouldn't feel like a habitat, it wouldn't feel like a ship, it would feel like a world, just one scaled to human life rather than cosmic accident. That idea sounds whimsical at first, almost toy-like. A planet like a snow globe, albeit still an incredibly large one. But once you leave Earth, size stops being sacred. Gravity, atmosphere, and surface area stop being gifts of nature and become engineering problems. And engineering problems have a habit of shrinking to the minimum size that still works. So today we're going to explore what happens when we stop asking how to build the biggest artificial worlds imaginable, and instead ask how small a planet can be while still feeling planetary. From gravity-equipped asteroids to shell worlds built around micro-black holes, we arrive at a strange but powerful idea: the microplanets. Small worlds, big numbers. We tend to imagine the future of space the same way we imagine the future of cities. Bigger skylines, vaster worlds, continents wrapped in steel and glass. And to be fair, that instinct is not wrong. Humanity has never built small for long. If there's room to expand, we usually do. But if you step back and look at how civilization actually grows, not how we dream about it, but how it behaves under economics, logistics, and human preference, you see a different pattern emerge. Not one giant city, but millions of towns. Not one global megastructure, but countless homes, businesses, farms, and neighborhoods, all stitched together into something that only looks monolithic from a distance. Space won't change that. If anything, it exaggerates it. And space, the one thing you are never short of is elbow room. The most common habitat in the future won't be the megacity cylinder or the planet-sized shell world, any more than the most common home today is a skyscraper or the default vehicle, an aircraft carrier. Those exist, and they matter, but most of civilization lives somewhere smaller. In space, that means rotating habitats the size of neighborhoods, towns, or even single extended households. Things you can build incrementally, move, sell, trade, upgrade, split, or abandon without collapsing entire civilization. In other words, space favors houseboats. A smaller rotating habitat isn't always just a place to live. It's a vehicle, a property, and a piece of infrastructure all at once. It can drift between orbits, dock with others, cluster into cities, or peel away and head somewhere new. That mobility matters. It pushes civilization away from single massive investments and toward huge numbers of smaller ones. And that's why, paradoxically, the era of the grandest artificial worlds must be the era of the smallest planets. And once you accept that, something strange happens. You realize that the distinction between habitat and planet starts to blur, because gravity does not care whether it comes from rotation or mass, it only cares about acceleration. We get ours by raw mass, 12 billion kilograms per square meter, or 1.2 million tons per square foot, which is a lot more than the typical 1 ton per square meter or foot, depending on how thick you want your dirt, that we imagine for your typical rotating space habitats. The thing is, there's a lot of mass we would want to store that isn't very useful for primary construction, like hydrogen and helium, which are extremely abundant and ideal as fusion fuel. That naturally leads to the idea of enormous fuel depots, so massive they can hold themselves together with their own gravity, so it cuts down on leaks. Add a solid surface layer on top, terraform it, and you've got what we call a shell world. These would never be the majority of your living area, but they would be pretty common, since in a fusion economy, the gravity well of Earth-mass planets isn't that big of an energy tax for storing fusion fuel, around a millionth of the energy it contains, and really helps prevent loss to leakage for very long-term storage. And there's a deeply unintuitive result hiding in that fact. If you want Earth-like gravity at the surface, the amount of mass you need scales with the surface area, not volume. Make a world half the radius of Earth, and yes, it's far smaller, but each square meter of ground still costs the same gravity-producing mass as it would on a full-sized planet. That means there's no inherent gravity penalty for bigger or smaller worlds. You don't save gravity by going big, you don't lose it by going small. And once you contemplate that, a radical idea becomes almost unavoidable. Why not build a planet bigger? Saturn's a big gas ball, the least dense planet, with about the same surface gravity of Earth already, and you could have a planet 100 times more spacious than Earth with one. The mass per living area stays the same, but the density inside goes down, inverse to radius. Twice as wide, half the density for the same surface gravity. That's where microplanets come in, and also the core problem with them. If you want Earth gravity at the surface, shrinking a planet means increasing its density. Cut the diameter in half, you need twice the density. Keep going and the requirements rise fast. So what to make it from? The densest ordinary matter we know of, osmium and iridium, top out at only about 4 times Earth's average density. That means using normal materials, the smallest Earth gravity world you can realistically build is roughly moon-sized. Anything smaller demands densities we simply cannot achieve with conventional matter. And even then, those metals are extraordinarily rare and valuable. Using them as a bulk planetary mass would be like terraforming the surface of an enormous iridium vault. Impressive, yes, but wildly impractical. Which is why planets get big so quickly and why replacing planetary mass with something far more compact changes the game entirely. Now, ordinary black holes do not help us here. The smallest naturally forming black holes are stellar mass objects, roughly 3 times the mass of the Sun, which would give you a world about 1,000,000 times Earth's mass and surface area, a literal megaplanet, and the origin of that episode's name. Interesting in its own right, but it's the opposite of what we want today. We're really after is high density without high mass. White dwarfs, neutron stars, and black holes all achieve that kind of compactness. But white dwarfs and neutron stars only exist at enormous mass, and there's no realistic way to keep them stable if you try to scale them down. Their physics simply does not allow it. Probably, you might be able to do it through extreme magnetic compression. And this raises another option. Stellar cores point towards a potential middle ground. Our Sun's core is about 150 times denser than water, roughly 30 times Earth's average density. In principle, you could magnetically confine matter at that density, essentially turning into a controlled fusion plasma, and so you could build a planet about 30 times smaller in radius, with roughly 1,000th of Earth's surface area. Now, that's not quite a microplanet, it's more of a milliplanet, but still an intriguing concept. More massive stars push this further. During helium burning, especially in later stages burning carbon, neon, and oxygen, stellar cores can reach densities tens of thousands of times to millions of times that of water. That would allow truly microscale planets, if you could hold that material together without stellar mass. And here's the catch. Fusion at stellar timescales is incredibly weak. Spread across its mass, the Sun produces less than a milliwatt per kilogram. Red dwarfs do even less. By comparison, a household generator puts out tens to hundreds of watts per kilogram. Commercial fusion would need to run vastly hotter and faster than stars do, not slower. So if you could magnetically confine matter at stellar densities without requiring stellar mass, essentially decoupling density from gravity, you get both a power source and a gravity source in one package. It wouldn't even need to be spherical. A donut-shaped tokamak reactor could generate gravity just fine, as long as it stays small compared to the planet itself. Even then, the planet does not need to be a perfect sphere. There's nothing sacred about that geometry, and there are some fun alternatives. If you can make that work though, you then also need a sweet spot of overall density to energy output, as you will keep raising the power to mass ratio as you raise density. Denser matter fuses faster. But you don't want to exceed what will keep your planet warm and lit. You don't have to limit your core to hydrogen and helium either. You can mess with fusion rates, slowing them while raising density by introducing other common elements like neon or even iron to tweak things until you have the Goldilocks zone of density needed for the microplanet you're trying to build with the power output you need to avoid burning everyone living there. This can probably be done, but if you can't pull that off, there's one object that has no trouble confining itself at any density or any mass scale: a black hole. If we can manufacture them, a topic we discussed many times, then we can set their mass almost arbitrarily, feed them slowly, and they become a long-term power source as well as a gravity generator. It would take eons for them to grow enough to noticeably change surface gravity, so any remodeling happens on geological timescales, not human ones. What is a microplanet and what is it like? So that brings us back to what a microplanet actually is. A microplanet is not a shrunken Earth in the conventional sense. It isn't a rocky ball with a molten mantle and a fragile atmosphere clinging on by sheer gravity. Instead, it's an artificial world whose gravity comes from a compact mass source, often a small black hole, surrounded by an engineered shell that provides the surface, the landscape, and the sky. From the ground, it feels planetary. You walk on curved horizons. Gravity pulls straight down. Rivers flow, weather forms, and buildings stand upright without spinning frames or Coriolis effects. Or at least different ones. But structurally, it behaves far more like a habitat than a natural world, and crucially, it has to. A small planet with Earth gravity at the surface still won't hold an atmosphere the way Earth does. Gravity drops rapidly with altitude when the radius is small. On these microplanets, a kilometer up, gravity is already noticeably weaker. A few kilometers higher, and it's a fraction of the surface gravity. Left open, air would thin, escape, or behave nothing like Earth's atmosphere. So instead of fighting that, microplanets embrace enclosure. They wear a shell. That shell does not need to be thick or opaque. It can be transparent, segmented, reinforced, and layered with radiation shielding and structural support. This crystal sphere or patchwork of domes around your microplanet holds the air in without interfering with the view. So it holds the air in, sets pressure independently of gravity, and decouples climate from planetary size. It also solves problems Earth never had: micrometeoroids, solar flares, orbital debris, and long-term atmospheric loss. And a small puncture or even a fairly large one does not mean all the air goes blasting away. There's still gravity, and we have tons of fixes for dome damage that apply, even quick ones or major holes. If you're worried about ruining the view, remember this: at planetary scales, thin supports fade into visual insignificance. A faint tint overhead, not a ceiling. The sky remains the sky. What you end up with is something that sits between worlds. Not a spinning ring, not a natural planet, something new. A planet you can build in batches, expand in rings, duplicate by the thousands, and scatter across the star system. And that brings us back to economics. If most people do not live in megastructures but in small habitats, and if planets themselves can be made modular, enclosed, and scalable, then the future may not be dominated by a handful of colossal artificial worlds. It may be dominated by millions of tiny ones, worlds built not to impress but to live in. So, could you buy one? Well, that depends. In a true post-scarcity economy, individual people might own something as large as an entire neocylinder, but they also have access to astonishing virtual landscapes, private spacecraft, and effectively unlimited personal space. What really matters is not the theoretical maximum, but what people would actually want as a place to live day to day. Somewhere you can go for a walk. Somewhere that feels like a place, not a project. That's one of the quiet advantages of both microplanets and rotating habitats. You can walk in a straight line and eventually end up back home. Micro, of course, just means small, but like mega, it's also a metric prefix with a precise meaning. A micro-Earth, taken literally, would have 1/1,000,000th of Earth's surface area, about 1,000th its radius. We could obviously go smaller or larger, but in this specific sense, we're talking about a world with roughly 500 square kilometers of surface area, about 200 square miles, 50,000 hectares, or 126,000 acres. That's room for several thousand of these 40-acre households we talked about earlier. In scale, that's comparable to an neocylinder or a smaller US county, especially the compact ones along the East Coast, Not sprawling places like my own Ashtabula County here in Ohio, which is about 7 times larger if you count the lake, and still several times larger even without it. Out west, of course, counties get bigger than some countries. From a construction standpoint, this scale looks very plausible, but also raises a practical question. How usable does it feel? A micro-Earth like this would be about 8 miles in diameter, with a circumference of roughly 25 miles. That's not something you can casually stroll around after dinner, but it's something most people could walk around in a day if they needed to. On a bicycle, it's trivial. For anyone even modestly augmented or transhuman, it's barely an outing. And at this scale, a lot of things start working in your favor. You have plenty of vertical room for a deep atmosphere and genuine and natural feeling weather. The planet only rotates once per day, so you don't get strong Coriolis effects or fast-moving storm systems driven by rotation. The surface speed is only about 1 mile per hour at the equator. Weather would not organize itself the way it does on Earth. But that's not a flaw, it's a design choice. You could wander nomadically and stay near the Terminator, always living in twilight, or stick to permanent daylight or permanent night if you preferred. Maybe live in a houseboat on a world-spanning lake that you simply slowly drift around to stay forever in the daytime. You could rely on natural sunlight, artificial lighting, or a mix of both. You'd almost certainly want a decent-sized reactor and thermal system to move heat and water around, shaping climate intentionally rather than letting it emerge by accident or needing high-powered mechanical intervention. And as these worlds get built by hundreds, thousands, or millions, you get very good at this. Landscape wouldn't just be decorative, they'd be functional. Grooves, ridges, forests, and outcroppings could guide airflow, trigger uplift, or break up wind without massive active pumping. And the ceiling itself, transparent, segmented, and engineered, could play a role in shaping weather rather than just containing it. At that point, climate stops being something you endure and becomes something you tune. Not perfectly, never perfectly, but well enough that a small world can feel as rich and alive as a large one. And that's the real theme here, not building the biggest possible world, but building worlds that feel right at human scale. So, could you go even smaller? Yes, especially if you're willing to live inside a proportionally larger atmosphere. Instead of a thin skin of air clinging to the surface the way Earth's does, you have an atmosphere whose scale height is comparable to the radius of the world itself, or even bigger. At that point, the transparent shell enclosing the planet becomes much more important. Without enough air depth, you lose the familiar twilight gradients, the reds, golds, and blues that come from the light bending through a long atmospheric path. Go small enough and you could also lose true clouds altogether. That's not unique to microplanets, it's the same issue we face on small rotating habitats. We already know how to fix it, or at least some options for doing so, with thicker atmospheres, engineered lighting, and carefully shaped ceilings. And the upside here is that you still get straight down gravity, without your neighbors ever being overhead the way they are in rings or cylinder habitats. In terms of mass, these worlds still scale the same way as the Earth-like planets. You need roughly the same gravity-producing mass per square meter of surface, and that mass has to come from somewhere. In practice, you'd likely feed them hydrogen or helium skimmed from gas giants or stars, materials that are abundant and not especially valuable for fusion fuel. And for the black hole itself, in our example microplanet, the one about 8 miles across, it would have roughly 1/millionth of Earth's mass. Physically, that black hole would only be about 18 nanometers wide, roughly 300 times the diameter of a helium atom. Feeding it matter is straightforward. You don't need anything exotic like a Kugelblitz generator to keep it alive. A black hole this massive but this small does not automatically mean dangerous tides. What matters is your distance from it, and your planet's radius is enormous compared to that hole. Just don't stick your head into it. And I would bet on an inner filling of helium or maybe even air at a density appropriate to keep it as a fairly hot gas that can push back against the shell your land is on to lower required structural strength. Depending on temperature, you might be able to go flying around in it, though that strikes me as needlessly dangerous, so presumably lots of people will do it. The black hole will barely touch that matter either. It would take eons to gain much mass without careful effort to aim atoms right down its tiny gullet, especially as its Hawking radiation provides outward pressure. It's small at that mass, but it's a small spot it's affecting too. Its Hawking radiation would correspond to a temperature of around 20,000 Kelvin, putting the peak emission in the ultraviolet around 7 electron volts, the nastier end of UV, the sort Earth's atmosphere already protects us from. But critically, it would only be radiating on an order of 10 microwatts. Energetic, yes, but so faint as to be effectively harmless. And with a lifetime measured in billions of trillions of years, feeding it for power would only extend that lifespan further. You keep this centered by magnetic fields or streams of matter you're running into it for power, so your black hole does not slowly drift off. You could embed one of these black holes in the center of a large asteroid, imported from some distant black hole factory and fed cheap mass along the way, but I suspect that wouldn't be the preferred approach. Imposing full Earth gravity on a natural microgravity asteroid would likely tear up its internal structure and erase the very landscape you might want to preserve. A better approach would be to start with a smaller asteroid, install a metal framework around the black hole, grind the asteroid down, and rebuild it around that core. Add your shell, water, and atmosphere, then sculpt the surface deliberately. Presto, a terraformed asteroid. Although there's a lot of other options and we should probably do an episode on it. And it's worth remembering that this is actually where the term terraforming comes from too. The word was coined in Jack Williamson's story Collision Orbit, which involved giving asteroids enough gravity to support seas, skies, and human life. By that original definition, adding gravity to an asteroid so it can hold an atmosphere absolutely counts as terraforming. Of course, you have some other way of stabilizing degenerate matter or generating gravity artificially, as classic science fiction often assumes. You could use that too. Though I'll always note that a gravity generator probably needs power to run, which makes it odd that starships in fiction lose power and life support simultaneously, yet nobody starts floating around. That's probably more for limited special effects budgets than imagination though. Microplanets sit at a fascinating intersection between habitats and worlds. They let us keep gravity, skies, weather, and horizons, while abandoning the assumption that planets must be rare, massive, and immutable. Whether built around black holes, stellar density cores, or technologies yet to be invented, they point toward a future where worlds are designed, duplicated, and customized at a human scale, not monuments to impress the cosmos, but places meant to be lived in. And if the future really does belong to small things repeated endlessly, then the galaxy may one day be filled not with a few grand artificial worlds, but with millions of tiny ones, each just big enough to call home. Cubeworlds and Polyhedral planets. Once we can build a microplanet around a compact source of gravity, there is no physical law requiring its inhabited surface to be spherical. Gravity prefers spheres, certainly, but megastructure engineering begins where nature's preferences end. We could build a cube, an octahedron, a dodecahedron, an icosahedron, or one of the more elaborate Archimedean solids. In a prosperous Kardashev Type II civilization, with trillions of habitats housing quintillions of people, there would likely be plenty of these strange, because we can, megastructures, built for novelty, prestige, or tourism. Such a civilization would also need places to store immense reserves of hydrogen, helium, and other raw materials. Rather than leave those depots as inert tanks, they could use that mass to generate ordinary gravity, and turn necessary storage infrastructure into dual-purpose novelty worlds. The first problem is structural. A cube built around a central mass would constantly try to collapse into a sphere. Its corners and edges sit farther from the center than the middle of each face, while gravity always pulls radially inward rather than straight down relative to the flat ground. Atlas pillars, orbital ring frameworks, or some other form of active support would be needed to hold those edges and corners outward. Gravity would also tilt as you walked away from the center of a face. At the exact middle, down points perpendicular to the ground. Near an edge, it points noticeably sideways toward the center of the world. Water and atmosphere would therefore tend to collect around these centers of the faces, leaving the edges as elevated, thinner-aired regions. There are several ways around that. We could distribute the gravity-generating mass unevenly, placing more of it beneath the edges and corners rather than concentrating everything at the center. We could curve each nominally flat surface into a shallow basin, so the local ground better follows the direction of gravity. Pumps, dams, pressure barriers, and active weather systems could keep water and air distributed where we wanted them. More advanced versions might even place separate compact masses beneath each face, producing several overlapping local gravity fields rather than one central pool. We'll discuss those options in more detail in our Flat Earth sections later. The easiest solution, though, may be enclosure. A transparent shell around each face, or one larger shell surrounding the entire world, would prevent atmosphere from escaping or pulling purely according to gravity. Each face could maintain its own air pressure, climate, and water cycle, much like our planetary-scale Worldhouse. The shell would not eliminate the gravity gradient, but it would keep low-gravity edges from becoming airless mountain ranges. For the smallest microplanets, that atmosphere might actually be larger than the world it surrounds. Consider a planet 10 miles across with an atmosphere studying 5 miles above the surface. Its transparent outer shell would be 20 miles across, twice the diameter of the inhabited world, and the enclosed atmospheric volume would be 7 times larger than the solid planet inside it. Gravity at the ceiling would also have fallen to only 1/4 of its surface value. On Earth, gravity has barely changed due to the top of the atmosphere. A 100-mile wide world with the same 5-mile atmospheric depth, or atmo-cubic depth in this case, would be much less extreme. Its shell would be 110 miles across, and gravity at the ceiling would remain about 83% of the surface gravity. So as these worlds grow, their skies begin to behave more naturally. Angular worlds also become easier to manage as we add more faces. A cube has only 6 broad squares and very severe corners. An octahedron has 8 triangular faces. A dodecahedron has 12 pentagons, while an icosahedron has 20 triangles and already resembles a rough sphere. More faces mean shallower angles between them, smaller variations in altitude, and gravity that remains closer to perpendicular across each face. Beyond those 5 platonic solids are the 13 Archimedean solids, traditionally associated with Archimedes. These combine 2 or more kinds of regular polygon for the surface while keeping the same arrangement at every vertex. The most familiar is the 32-sided truncated icosahedron, 12 pentagons and 20 hexagons, better known as the traditional soccer ball pattern. Suppose one of those soccer ball worlds measured 10 miles from one side to the opposite side. Each pentagonal face would cover about 7 square miles, and each hexagonal face about 10.5, almost 7,000 acres or 2,700 hectares. Every face could hold a town, lake, forest, private estate, or small nature preserve, while the ridges between them formed mountain chains or structural walls. A more elaborate example is the truncated icosodecadahedron, sometimes called the Great Rhombi icosodecadahedron. It has 62 faces, 30 squares, 20 hexagons, and 12 decagons. It is the Archimedean solid with the greatest number of faces, and from a distance it would look far more planet-like than a cube. At only 10 miles across, its smallest square faces would each cover about 0.57 square miles, around 150 hectares or 360 acres, a plausible single-family estate, especially in a post-scarcity civilization. Its hexagons are larger at about 1.5 square miles, and its decagons about 4.4. That is already enough for individual estates, villages, parks, and small lakes, though some faces would be cramped if we wanted complete communities. Increase it to 20 miles across and the area rises with the square of the diameter. Each square becomes roughly 2.3 square miles, each hexagon about 6, and every decagon nearly 18. Now even the smallest face has room for multiple households, farmland, woodland, and perhaps a small lake, while the larger faces could support towns and small cities. At 100 miles across, the square faces would each hold about 57 square miles, and the hexagons nearly 150, and the decagons over 440. Every face would be a genuine geographical region, more like a county than a building lot, with its own cities, rivers, coasts, and climate. That raises another reason to build polyhedral worlds besides novelty and tourism: privacy. On a spherical planet, the horizon gradually hides distant places. On a polyhedral world, an edge provides a sharper boundary. From the middle of one face, the neighboring landscape bends abruptly away and disappears from ordinary view, but the horizon remains sharp even as you walk toward it, hiding your neighbors even on hilltops close to your boundary. A household might own an entire face, able to see its own forests and fields, but not the homes on the other sides. Larger worlds might give each face to a different town, nation, ecosystem, or cultural group. The edges could carry roads, railways, reservoirs, power lines, or defensive barriers. The vertices might house spaceports, reactors, elevators, or low-gravity recreation zones. Crossing from one face to another could feel less like crossing a county line and more like passing between separate worlds. The minimum size of a polyhedral planet might therefore be determined not by engineering, but by preference. How much land do you want before your neighbors vanish beyond the edge? Do you want one household per face, one village, or one nation? A sphere uses mass efficiently. A polyhedral world uses geometry to divide space in distinct places, and for a civilization wealthy enough to manufacture planets, that may be reason enough. What if the key to colonizing the cosmos wasn't reshaping planets, but enclosing them? Instead of waiting centuries for a thin Martian atmosphere to form, What if we could create an Earth-like world overnight by sealing entire landscapes beneath an artificial sky, transforming dead rock into thriving ecosystems, one dome at a time? Imagine standing on Mars, breathing fresh air under an endless vaulted sky, not because we painstakingly terraformed the planet, but because we built an atmosphere of our own, enclosed in vast planetary domes. When we think about colonizing other worlds, the first thought is often terraforming, a slow, uncertain process of reshaping a planet's climate and surface over thousands of years. But what if we didn't have to wait? What if, instead of sculpting a world to fit us, we built the environment we needed from scratch? More than that, what if we weren't even limited by the natural gravity of a planet or moon? This is the concept of a Worldhouse, a planetary-scale enclosure designed to create a stable, controlled biosphere on an otherwise uninhabitable world. Why spend 1,000 years coaxing Mars into being habitable when you could give it a space-age greenhouse overnight? Instead of waiting for nature to cooperate, we engineer a perfect climate, enclosing regions, or entire planets, within vast shells that trap atmosphere, regulate temperature, and shield the surface from deadly radiation and cosmic debris. It may sound like science fiction, but the idea has deep roots in real-world engineering, and it may be far more practical and effective than classic terraforming. It also allows for a patchwork quilt approach, beginning with early domed colonies on a place like Mars, gradually expanding one dome at a time until they merge into a vast, enclosed world. From Buckminster Fuller's geodesic domes to experimental biosphere projects, humans have long explored the challenge of building self-sustaining environments. The Worldhouse is simply the ultimate version of that idea, turning entire planets into engineered ecosystems. In this episode, we'll explore how such megastructures could be built, starting with domes over key regions, expanding like a growing quilt across the planet, and eventually sealing in entire worlds beneath an artificial sky. We'll also look at fully enclosing asteroids, perhaps even using miniature black holes for artificial gravity. And finally, we'll ask the big question: could Earth itself one day be enclosed in a Worldhouse? And would we want it to be? The Worldhouse concept. Terraforming has long been seen as the gold standard for making other planets livable, and we will be doing a deep dive of the options in our terraforming compendium in a month. But the truth is, terraforming is a slow, unpredictable, and nearly irreversible process that in most cases will still result in a less Earth-like environment than a space habitat like an O'Neill cylinder or a Stanford torus. Terraforming is nature's way, slow, messy, and unpredictable. Space habitats and para-terraforming options like a Worldhouse is more humanity's way, fast, efficient, and with a warranty from the manufacturer. Even under ideal conditions, reshaping an entire world's atmosphere, temperature, and ecosystem would take centuries, if not millennia, and that's assuming we could even get it right. What if, instead of trying to change a planet, we simply enclosed it? This is the idea of a Worldhouse, a concept originally proposed by Paul Birch, a physicist and megastructure theorist from whom we get some of the channel's favorites like the Orbital Ring, the Shell World, and the mind-bendingly huge Birch Planet. A Worldhouse is an artificial planetary enclosure, a giant transparent shell covering the surface of a planet, moon, or even an asteroid, trapping an atmosphere and controlling climate with precision. Instead of slowly modifying an entire planet's environment, a Worldhouse lets us skip straight to the finished product, engineering a stable, Earth-like biosphere inside a protective megastructure. In many ways, it is the ultimate extension of para-terraforming, the alternative approach to settling planets compared to classic terraforming or bioforming, which relies on the idea of permanent use of megastructures and planetary maintenance, which can often seem less ideal than putting all the work in up front by changing a world or its organisms. But in practice, all these methods require maintenance. Even Earth is not static, and it's a good reminder that while terraforming means to make a planet more Earth-like, what we really mean is more human-optimal, as while we might want some very harsh climates like Antarctica, or even alien ones, that's not what we would expect the main focus to be. A Worldhouse offers several key advantages over terraforming: instant atmosphere and climate control. Instead of waiting for oxygen levels to rise naturally, we could engineer the perfect atmospheric balance from day one. Temperature, air pressure, and humidity would all be adjustable at will. Instead of needing tens of kilometers of air, you might only need tens of meters, depending on how high you want your ceiling, and you could raise that over time if you wanted to. This is doubly handy on Mars, whose low gravity means you would need even more air per area than Earth has to achieve normal pressure by simple weight of air above, as it weighs less. 2. Radiation and micrometeoroid protection. Unlike an open atmosphere, a Worldhouse physically shields the surface from harmful cosmic radiation and space debris. It's like giving a planet SPF 1 million. This is critical for places like Mars and the Moon, which lack strong magnetic fields to protect against solar and cosmic rays. Why worry about solar storms when you've got an all-weather, all-terrain force field? Paraterraforming like Lagrange point magnetic deflectors and Worldhouses give us those options. 3. Global engineering. Weather, storms, and even day-night cycles could be customized inside a Worldhouse, ensuring optimal conditions for life. Want a world with eternal spring? A Worldhouse could make it happen, even on a planet too far from its sun to have liquid surface water. 4. Less energy, faster results. Classic terraforming might require thousands of nuclear detonations, cometary bombardments that wreck the planet's surface worse than any nuclear war, massive atmospheric processing, or centuries of waiting for gases to accumulate. A Worldhouse, by contrast, is a mechanical solution. Once built, it works instantly and can be gradually expanded. And number 5, doesn't require gravity or thick atmosphere. Unlike traditional terraforming, a Worldhouse doesn't need a planet with strong gravity to retain air. Even an asteroid or low-gravity moon could support a breathable environment inside an enclosed shell. While working on episodes like this, I spent a lot of time imagining how we might build healthy ecologies in future space habitats, often while driving my tractor around my own farm. We grow several things here and keep chickens and honeybees, so questions about how we shape environments and care for the animals within them feels personal to me. That's what drew me to FarmKind, a non-profit donation platform for farmed animal welfare. They research evidence-based charities working to end factory farming, then make it easy to support several at once, without judging anyone or telling them what they should eat. And it is working. One of the charities they recommend, the Humane League, helped push McDonald's, Nestle, and Walmart into cage-free commitments, and American cage-free hen numbers have climbed from 4% to over 40% in under 20 years. Just 50 cents a day, that's $15 a month, can help nearly 350 animals in a year. FarmKind takes no cut and shows the estimated impact of each donation so you can see exactly how many animals your gift can help. Use the link below and code ISAAC to boost your monthly donation by up to 50%. How would a Worldhouse be built? The simplest version of a Worldhouse would start small, perhaps a series of interconnecting domes covering key regions, much like a city built under a giant bubble. Over time, those domes could be expanded outward until they fuse together, forming a continuous planet-wide structure. Start with a village, expand to a city, and before you know it, you've got an entire planet wrapped up like a sci-fi Christmas present. We would expect rebuilding in many cases too. We do not build for permanence. It's often not only uneconomical but counterproductive. We might be able to make some ultra-long-lasting building materials in the future. Graphene-infused cement or even domes made of pure artificial diamond. It's just carbon after all. But we basically rebuild every part of human civilization on something like a 10 to 100 year timeline. Stuff breaks, plus we like to move things or try new styles and purposes. Even when we don't rebuild, we often put in equivalent maintenance to that effort. So you need not start with a giant dome over one town. You build your patchwork quilt of smaller domes, then decide to build a new big one over the whole place, and recycle those smaller domes when you're done. Don't worry about a dome breach, we'll discuss that later, but you don't need to leave domes behind inside for backups, as odds are a very automated and high-tech civilization built on another world would have included airtight structures or rooms in the first place. The shell itself would likely be ultra-lightweight yet immensely strong, made of advanced materials like transparent aerogels, providing insulation while allowing natural light, graphene-reinforced composites, lightweight and incredibly strong, metallic or polymer-based membranes, able to regulate heat and pressure while being flexible enough to cover uneven terrain. Artificial diamond. We can produce diamond rather cheaply already, and it's likely a process that scales well. Transparent ceramics and alloys. We already have many transparent materials far more robust than classic glass that could rival the transparent aluminum from Star Trek. The future may bring us even better options. The classic sci-fi trope of a dome shattering like an old window has never been a real concern. In reality, no one would construct a single giant bubble. It would always be made of smaller, replaceable segments or panes for easy maintenance and repairs. You might worry that steel girders and segmented panes would ruin the view of the sky, but that's hardly critical, and in practice, they wouldn't be noticeable from a distance. The human eye can only resolve details down to about an arc minute, meaning thin structural supports or a mesh-reinforced window would simply act like a light shade or tinting, rather than blocking the view. For instance, at 1,000 meters high, the smallest visible width would be about 30 centimeters, just under a foot, and for a mile-high dome, about 47 centimeters, a foot and a half. Double the distance and the visible width doubles, halve it and the width halves. That's small enough that even a segmented dome with wide steel girders would still appear crystal clear, especially with modern or future super-strong materials. We might contemplate folks with genetically or cybernetically enhanced vision being able to see the mesh still, but augmentation has its downsides. Additionally, reinforced materials like graphene or metal mesh embedded in the panes could give the dome a damage profile similar to armored glass or windshields, leading to spiderweb cracks and leaks rather than catastrophic failure. We also have rapid repair technologies for sealing breaches, some of which we discussed in previous episodes, like the domes of Mars. Also for leaks, blowing a meter-wide hole in a mile-wide dome would not cause instant catastrophe. Despite what Hollywood tells you, a crack in a space dome isn't going to suck people out like a spaghetti noodle in a vacuum cleaner. You wouldn't have seconds or minutes to live, or even hours. A hole that size would take weeks to depressurize, plenty of time to slap some high-tech space duct tape on it. And long before that, automated systems could detect and patch the breach within seconds or minutes. Needless to say, this could get pretty high-tech, but even a simple automated mortar could launch a sturdy, airtight patch, like a high-tech beach ball, directly onto the hole to seal it. Another option might be a membrane with magnetic edges designed to stick over the breach instantly. On the more advanced side, we could imagine a multi-layered dome with automated self-repair systems, integrating functions like air filtration, water reclamation, and structural reinforcement. In other words, a wardhouse wouldn't just be durable, it could also be self-sustaining. Advanced automation and environmental controls might not just manage structural integrity, but also maintain a stable, thriving biosphere inside. Beyond just keeping the air in, the dome itself could serve as an essential component of the planet's life support system. Solar power collection could be integrated directly into the shell, providing limitless energy while also acting as a climate regulator, absorbing or reflecting sunlight as needed. The interior environment would be carefully engineered for long-term stability, with artificial weather patterns, controlled precipitation, and tailored ecosystems for food production and habitation. But a wardhouse does not have to be built all at once, and in fact, trying to cover an entire planet in a single step would be wildly impractical. Instead, we can start one dome at a time, gradually expanding until, eventually, an entire world is enclosed beneath an engineered sky. And while a wardhouse is usually imagined as a closed shell, it doesn't have to be completely sealed. Ventilation openings, radiation-absorbing windows, and even adjustable portals could allow for some interaction with the external world, just without the risks of full exposure to vacuum or a hostile atmosphere. In a moment, we'll explore the step-by-step approach to wardhouse construction, the idea of covering a planet one dome at a time, like a growing quilt of interconnected habitats. But before we move on, it's important to emphasize that not only are these structures potentially diamond-hard and safer to live in than an open planetary surface, but also that the idea that para-terraforming is inferior to terraforming due to maintenance needs is highly dubious. Earth is not static, nor are its environments and ecosystems, but even if they were, very few planets will ever be capable of supporting a true Earth-like conversion without the need for continuous adjustments. Factors like lower gravity, stronger solar winds, or different day and year lengths will all exert pressure to degrade a terraformed world over time, requiring ongoing corrections. And the greater the difference from Earth's natural conditions, the faster those changes will erode the terraformed state, introducing what we might call a metaphorical wobble in the balance of the environment. We explore this idea in detail in our episode on pancosmorial theory, which examines how planets can slowly unterraform themselves without constant maintenance. But even without that risk, consider this. If you're trying to double the amount of sunlight reaching a planet, which is the better approach? Should you maintain millions of square miles of orbital solar mirrors to increase its light intake, or should you accept colder temperatures, increase the carbon dioxide levels, and engineer all life forms and ecosystems to adapt to lower light, lower temperatures, and a higher greenhouse gas ratio? Planets leak air naturally or sequester it over time, and full terraforming would take thousands of years regardless. If you could sustain that long, grueling effort on a mostly dead world, then surely maintaining a much smaller, more efficient paraterraforming system on a thriving, enclosed planet would be a far easier and more cost-effective solution. This isn't a sci-fi story either. There's no reason to assume a civilization advanced enough to terraform a planet is, once that's completed, going to abandon their technology. They would already know that planets are only metastable, and their culture would probably revolve heavily around making that world livable and keeping it that way, so it would be a weird thing for them to overlook. That emerging culture is also why a patchwork approach seems more viable, as a civilization raised under domes for a few centuries might feel a bit hesitant to live under open sky and be quite comfortable with domes and prefer to expand them piece by piece. The quilt approach, expanding a worldhouse over time. A full planetary enclosure might sound like an overwhelming engineering challenge, but the beauty of a worldhouse is that it doesn't have to be built all at once. Instead of constructing a single massive shell, we take an incremental approach, covering a planet one dome at a time, like an expanding quilt of interconnected habitats, or the roads and highways of a newly settled region, expanding and improving as needed. This method, sometimes called patchwork paraterraforming, allows for gradual expansion and adaptive development. It begins with smaller, localized domes, covering key settlements and resource hubs, then expands outward as technology advances and populations grow. Step 1. Establishing the first domes. The first phase would likely start with small, self-contained domes, built in strategic locations such as crater bases, providing natural structural support, deep canyons or valleys, offering shielding from radiation and storms, lava tubes or subterranean networks, already partially closed. These domes would serve as early footholds, supporting colonists, agriculture, and industry, while protecting against hostile environments. They could be built using local materials, regolith, ice, or carbon composites, to minimize launch costs and logistical challenges. Step 2. Interconnecting and expanding the network. Once multiple domes exist, the next logical step is connecting them. This can be done through pressurized tunnels and transport corridors, transparent or semi-transparent archways, expandable modular domes merging into larger enclosed regions. Done properly, this can even allow flow between locations by weather, ecology, and the flora and fauna that need to migrate or swap DNA to avoid genetic bottlenecking. As more domes are linked, they could share resources such as atmosphere processing, power grids, and water recycling, reducing overall maintenance costs and ensuring redundancy in case of failures. Step 3. Merging domes into a continuous shell. At a certain scale, the distinction between separate domes and a full planetary enclosure starts to blur. Overlapping segments and reinforced superstructures could gradually create a continuous worldhouse, covering the entire planet, moon, or asteroid. By this stage, the system would be self-sustaining, with climate regulation, artificial weather, and optimized energy management ensuring a stable biosphere. Advantages of the quilt approach. Scalability. You can start small and expand as needed. Adaptability. Settlements can be built where conditions are most favorable. Redundancy and safety. A single breach wouldn't compromise the entire system. Lower initial investment. No need for a full enclosure up front. Growth happens organically. This gradual approach makes worldhouses practical and economically viable, rather than a futuristic fantasy requiring impossibly vast resources all at once. To put things into perspective, it would take around 5,000 comets, each the mass of the asteroid that ended the dinosaur era, to match the mass of Earth's atmosphere, and over 1 million to equal our oceans. Imagine one crashing down every day for 1,000,000 days or so. While such a task is possible, it demands vastly more material than would be needed to construct an entire planet covered in large domes, and is likely far more initial effort than simply maintaining those domes for 1,000,000 days or 2,700 years. This approach also means you can have climates that wouldn't necessarily be viable on a terraformed planet without disrupting your neighbors' ecosystems, and many a future planet is likely to have many different nations on it that don't agree 100% on terraforming end goals and timelines, and para-terraforming lets you alter your own area with little or no impact on your neighbors, whereas if Alaska decided to add solar mirrors to warm itself or Arizona solar shades to cool itself, there'd be massive knock-on effects to everyone nearby, far beyond what a collection of domes would cause. More importantly, in the terraforming scenario, you are attempting a world-altering effort with a small population and limited infrastructure. In contrast, with para-terraforming, you are maintaining a more modest and efficient system using the resources of an already thriving civilization. Expansion happens as needed, so a dome the size of a county, or even an entire state, is not being maintained by a mere 100 settlers, but by thousands or millions of inhabitants. Speaking of that, let's explore how partial enclosures, such as megadomes over entire valleys or craters, could provide a middle ground between small-scale habitats and full planetary encapsulation. Partial enclosures, megadomes over key regions. Not every worldhouse has to be a complete planetary shell. In many cases, partial enclosures, such as massive domes covering entire valleys, craters, or regions the size of a country, might provide a middle ground between small-scale habitats and full planetary encapsulation. These megadomes would allow for localized terraforming, creating stable, Earth-like environments in otherwise inhospitable landscapes. The case for megadomes. A full planetary enclosure is an ambitious, long-term project. The large-scale dome of a single region could be a more immediate and practical solution. These enclosures would create Earth-like conditions locally, allowing settlements and agriculture without waiting centuries for full terraforming, shield against radiation and micrometeorites, especially for low magnetic field worlds like Mars or the Moon, offer precise climate control, preventing extreme temperature swings and dust storms, require far less material and energy than a full worldhouse, making them easier to construct and maintain. Certain locations in our own solar system stand out as ideal candidates for megadomes. Let's review some. Noctis Labyrinthus, a natural foundation for a Martian worldhouse. One of the best locations for a large-scale enclosed habitat would be Noctis Labyrinthus, a vast maze of canyons on Mars near Valles Marineris. This terrain provides natural walls, reducing the material required for enclosure while offering protection from wind and surface-level radiation. A single interconnected dome system could transform this region into a sprawling Martian metropolis, complete with artificial rivers, forests, and farmland beneath a controlled sky. Other locations that could be enclosed include Hellas Basin, a massive impact crater on Mars, naturally suited for an enclosed environment. Lunar lava tubes. Deep underground tunnels on the Moon could be pressurized and sealed off with minimal construction effort. Worldhouses are not limited to domes above ground. We could have immense underground caverns and subterranean cities and ecosystems too. Europa's subsurface ocean entrances. Enclosed habitats could allow human exploration of Europa's subglacial ocean without constant exposure to radiation. Domes can go undersea too, and we might imagine diamond-hard snow globe-like habitats floating in oceans that also expand and connect to others over time. Engineering a megadome. A megadome covering an entire region would need to be both lightweight and incredibly strong. Some possible designs include graphene-reinforced aerogels. Extremely lightweight, transparent, and strong, these materials could form the primary enclosure layer. Tensile cable-supported domes, a mix of suspension bridges and geodesic dome designs, allowing flexible, segmented construction. Layered shield structures, using multiple thin layers instead of a single thick dome, reducing the risk of catastrophic failure. Enclosing asteroids, the micro worldhouse. Not every worldhouse needs to be built on a planet or moon. In fact, the term terraforming was originally coined by Jack Williamson in a short story about altering a small asteroid to support life. Some of the most practical applications of the Worldhouse concept could involve fully enclosed asteroids to create self-contained micro-worlds. Instead of simply mining asteroids for raw materials and abandoning them, we could hollow them out, seal them, and transform them into habitable environments, trapping air and water inside while offering a stable radiation-shielded ecosystem for long-term colonization. Why settle for a boring, dusty asteroid when you could turn it into a luxury space condo? Alternatively, smaller rotating habitats could be placed inside asteroid hollows or within surface craters, taking advantage of the asteroid's natural shielding against micrometeors and cosmic radiation. A contained, pressurized asteroid could also make mining far more efficient, as any dust and debris would remain trapped within the enclosure rather than being ejected into space as hazardous micrometeors. With the right engineering, an asteroid could become more than just a source of raw materials. It could be a thriving, adaptable settlement. But this raises another intriguing possibility, using asteroids as microgravity environments. While many enclosed asteroids might feature full-gravity, rotating habitats inside or nearby, others could support ecosystems specifically adapted to low gravity, thriving within a glass shell or a series of interconnected surface domes. These domes could expand over time into a patchwork Worldhouse, and given the much smaller size of asteroids compared to planets, this process could happen far more quickly. Such habitats could be fascinating places to visit, offering an entirely different kind of living environment. This begs the question, if Worldhouses might be the norm for every planet we settle, and even many a moon or asteroid, would Earth be the only place without them? And might Earth itself become one? Earth as a Worldhouse. Could we enclose our own planets? A few years back, when we explored settling the Lagrange points and cislunar space, I pointed out one of the major challenges of living near Earth, the Van Allen radiation belts. While space habitats would likely be heavily shielded against this radiation, spaceships traveling to and from Earth would need much thicker shielding, which adds mass and fuel cost to every trip. It also adds great cost to places like agricultural habitats, where you still need more dirt and water for shielding than you really need for agriculture. In the future, we may develop vastly better radiation shielding, or even treat radiation-induced illnesses like minor colds, reducing these concerns, but we might also take a more proactive approach, eliminating the radiation in those belts altogether. The Van Allen belts are caused by ionized particles from the solar wind that get trapped by Earth's magnetosphere, forming a persistent radiation zone. The same issue exists for Jupiter, whose far stronger magnetosphere makes settling its Galilean moons particularly hazardous. One solution might be to enclose those moons in Worldhouses to protect them from radiation, but another option would be to actively drain the charged particles from the belts, a process that could be both practical and profitable if we could collect and repurpose them. Alternatively, we might install massive magnetic deflectors at Lagrange points to prevent these radiation belts from forming in the first place. This is yet another example of paraterraforming at the megastructural scale, demonstrating that even Earth could benefit from planetary scale engineering. And if we were willing to go that far, why not take it to the next step? If we're already considering ways to modify Earth's magnetosphere to reduce radiation exposure, then why not go all the way and give Earth its own Worldhouse? If Worldhouses become the standard for planetary settlement, why would Earth be the exception? We often assume our homeworld is perfectly suited to life as it is, but even Earth has harsh environments, extreme weather, and energy inefficiencies that could be mitigated with large-scale enclosures. Rather than a single vast shell covering the entire planet, a more practical approach might be to start with enclosed megacities in colder climates, where greenhouse-like domes could offer better temperature control, pollution management, and year-round food production. A settlement in Antarctica or Greenland, for instance, could gradually expand its domes, patchwork style, until entire regions became enclosed. Over time, this same approach could extend to cities worldwide, creating a network of interconnected environments, a Worldhouse not for survival, but for optimization. The future of Worldhouses. The Worldhouse concept challenges our traditional ideas of planetary settlement. Instead of reshaping a world over thousands of years, we could build habitable environments instantly, enclosing planets, moons, or even asteroids in engineered biospheres. From small domes over Martian craters to massive enclosures covering entire planets, the possibility for controlled, adaptable habitats are nearly limitless. as are hybrids with other para-terraforming and space settlement options. But more than just a tool for expansion, Worldhouses might be essential for long-term sustainability. Even a terraformed planet needs upkeep, and as we explored in pancosmorial theory, planets can unterraform over time. A Worldhouse, on the other hand, allows for precise environmental control, ensuring that a civilization's efforts to build a livable world are never undone by nature's slow but inevitable drift. They create a more robust environment, not just against the erosion of time, but even against the hostile activity by enemies foreign and domestic. As we look to the future, the idea of Worldhouses raises bigger questions. Will every settled world, moon, or asteroid eventually be enclosed? Could our own planet one day become a fully optimized, engineered environment? And if so, how much control should we have over nature, and how much should we leave to chance? Regardless of the answers, one thing is certain. If humanity is a spread across the cosmos, it will not just be the natural environments of other worlds that shape us, but the worlds we choose to build for ourselves. Terraforming tries to make nature do the work for us. Worldhouses let us roll up our sleeves and get it done ourselves, and just the way we want it. Bowlhabs and Rotacities. A Worldhouse can place an Earth-like environment over a low-gravity world, but does not change the gravity underneath it. Mars still pulls with only 38% of Earth gravity, and the Moon with about 1/6. We might adapt ourselves to those conditions, add compact masses, or some more advanced form of artificial gravity, or choose a simpler solution. Spin the city. A Rotacity, often called a Bowlhab, is a rotating settlement most easily built inside a crater or artificial basin on a world with little or no atmosphere. Natural gravity pulls downward toward the planet, while rotation produces centrifugal acceleration outward from the bowl's axis. Tilt the floor so that it sits perpendicular to the combined acceleration, and the residents experience both effects as a single apparent gravity pressing them into the ground. Because those two accelerations act at right angles, they do not simply add up. Their combined strength is found with the Pythagorean theorem, the square root of the natural gravity squared plus the spin gravity squared. A world providing half a g downward and habitat producing another half g sideways will therefore give about 0.71 g, not 1 full g. To reach Earth normal gravity on Mars, where the planet already supplies 0.38 g, rotation must provide about 0.925 g sideways. The local floor would slope roughly 68 degrees above the horizontal, or 22 degrees from the vertical. On the Moon, natural gravity supplies only about 0.17 g, so rotation must provide roughly 0.986 g. The floor would rise about 80.5 degrees above horizontal, less than 10 degrees from vertical. A 1G lunar rotacity would therefore resemble an immense upright cylinder or urn more than a shallow bowl. The Martian version could remain somewhat broader, while settlements willing to accept lower gravity could use gentler slopes and slower rotation. The complete habitat would not normally be a simple cone. A conical floor works well for a narrow rotating band whose radius is much greater than its width, since the effect of gravity changes little across it. Across a full city, however, centrifugal acceleration increases with the distance from the axis. Near the center it is weak, so the ground can remain nearly level and local gravity dominates. Far outward, the floor must curve progressively upward as rotational gravity grows. The resulting surface resembles a bowl or paraboloid, much like the curved surface water adopts inside a spinning container, like your washing machine. Gravity would therefore vary from district to district. Central neighborhoods might preserve the Moon or Mars's natural gravity, making them useful for recreation, spacecraft handling, warehouses, or industries that benefit from lighter loads. Residential areas farther outward could approach Earth normal gravity. Roads and transit lines might circle the bowl in concentric bands, each offering a different balance between natural and rotational gravity. Rather than spin one continuous structure, engineers might install several broad rotating rings inside the same crater. Each could turn at its own speed and carry a floor anchored for its preferred gravity. That would simplify construction, allow districts to operate independently, and prevent maintenance on one ring from shutting down the entire city. So too, you could have a number of these bowls neighboring each other to add living space, and probably a wider settlement of lower gravity facilities with the Bowlhab as the main residence. The crater is optional but provides a convenient foundation, as well as shielding and a containment area, while a stationary dome above could retain atmosphere and protect the rotating settlement from radiation and debris. Unlike a floating habitat freely in space, a Rotacity could draw power, water, raw materials, and structural support directly from the world beneath it. Alternatively, to avoid atmospheric turbulence, you might affix the dome to the rotating bowl itself, which also avoids drag issues. Bowlhabs offer a useful compromise. We need not reshape an entire planet, or accept whatever gravity nature happened to provide. We can close a region, spin the inhabited landscape within it, and tune gravity neighborhood by neighborhood. But even these cities still begin with a planet or moon. Our next habitats abandon solid worlds almost entirely, using immense shells of gas and structure to create artificial worlds floating freely in space. Ederworlds. So how big can this go? There's a couple directions that allow truly epic size. Ederworlds, sometimes called bubble worlds or Ederspheres, are habitats on a scale so vast they make even O'Neill cylinders look modest. The idea came from Danny Eder, who asked a simple question: what's the largest orbiting habitat humans could build? Instead of relying on spinning walls and structural strength, his insight was the gas itself has mass and generates gravity. If you trap a giant cell of hydrogen or other light gas, its own self-gravity can counteract the pressure trying to blow it apart, which is the case for most gas giants and stars, of course, while in this case an outer shell or cap floats upon it, containing the atmosphere within it but not under any great strain. The result is a self-gravitating bubble, a habitat where gravity and pressure balance each other out without requiring impossible materials or tensile strengths. Scaled up, this creates megastructures tens or even hundreds of thousands of kilometers across, soap bubbles in space. The default concept calls for a sphere not much smaller than the entire Earth-Moon system, just under 500,000 kilometers in radius. This is surrounded with a mostly hollow steel shell a couple thousand kilometers thick, with about 50 meters of thick steel shell on the extreme outside, serving as weight against the hydrogen gas and protection against radiation and micrometeors, and enemy attack for that matter. Gravity varies with depth, and indeed is much lower inside the inner shell, as most of the gravity is coming from that steel shell, and doesn't count toward the gravity in the inner volume. As a reminder, any evenly distributed shell of mass generates no actual net gravity on things inside that shell, so a shell of vast mass but hollow would let you float around inside it in microgravity. The gas inside that shell does exert gravity, at least at depths lower than the object being pulled on. But in the primary habitation shell on the outside, with the steel exerting gravity, you're looking at about 2% of normal Earth gravity. The surface area of this sphere is more than 10,000 times that of Earth. A single Ederworld is expected to have multiple layers in open environment, and could have more living area than 1,000,000 Earths, with its interior atmosphere stacked in layers dozens of kilometers thick, like Earth's own atmosphere or even thicker. While the gravity inside is weak, it is not non-existent, and the design allows for countless sub-habitats suspended in the airy depths, floating cities, ring dwellings with spin gravity, or entire artificial ecosystems. Bubble habitats. Now, a variation on the Ederworld is a simple bubble filled with breathable air and moisture, and floating or suspended habitats or rocks, and this works easily and intuitively enough at smaller sizes, even into several hundred miles across. But let's consider way bigger. If you want an environment with 1% of Earth's normal gravity near its surface, and without a big thick shell, filled with normal air at normal density, then you again have an object similar in scope to the whole Earth-Moon orbit, with a radius of 286,000 kilometers. This is only a mass around that of Neptune, 20 Earth masses, but spread over space 4 times wider or 64 times larger in volume. Your issue at this scale is keeping it from collapsing into itself as a gas giant, and a rather weird one of oxygen and nitrogen rather than mostly hydrogen and helium like natural ones. Your real issue here is that you don't need vast depth. About 1,000 miles of air is already immense. Think of a parallel to our earlier hydroshell concept, where a hollow shell is covered in a vast ocean. In this case, though, you'd have 2 concentric shells with air sandwiched between them, separated by about 1,600 kilometers or 1,000 miles. That's an order of magnitude deeper than Earth's atmosphere, with the inner shell itself spanning some 2.2 million kilometers in radius, over 3 times wider than our Sun, using around 20 Earth masses of air. At the top of this atmospheric shell, which we might call an atmo shell or bubble shell, gravity would be just 0.0168% of Earth normal, fading to near zero at the bottom. Still, it's enough to build all sorts of suspended habitats. rocky platforms hanging from the ceiling or structures rising up on pylons from the floor, stalagmites and stalactites or chandeliers. It's an environment where up and down lose meaning, yet the faint tug of gravity gives just enough anchoring to work with. To put that in perspective, a person with a mass of 100 kilograms, about 220 pounds, would weigh just 17 grams, roughly 4/100ths of a pound. Drop an object from head height and in a vacuum, it would take close to a minute to hit the floor. In air currents, it could drift far longer. And remember, that's in the strongest part of the gravity field, right at the top of the shell, so you could definitely strap on a pair of wings and flap around. I think you would spin these slowly too. One this size could not be spun once a day without creating a huge centrifugal force far stronger than Earth's gravity, but in an outward direction. Cloud and Chandelier cities. Bubble habitats float through empty space. The same basic idea becomes easier when a planet already provides an atmosphere to float in. Cloud cities or sky cities use buoyancy or aerodynamic lift rather than orbit or anti-gravity, allowing entire settlements to hang in the skies of worlds whose surfaces are hostile, inaccessible, or non-existent. Venus is the classic example. Roughly 50 kilometers above its surface, the pressure and temperature are surprisingly Earth-like, even though the clouds remain acidic and the world below resembles the inside of an industrial furnace. Better yet, Venus's atmosphere is mostly carbon dioxide, so ordinary, breathable air is itself a lifting gas. A sealed habitat filled with an Earth-like oxygen and nitrogen mixture would float much as a helium balloon does here. That lets an inhabited volume serve as part of the lifting system, rather than being dead weight suspended beneath it. Large structures are especially attractive because buoyant volume grows faster than surface area and structural mass. Vast geodesic balloons, sometimes called Cloud-9 spheres, might carry cities, farms, lakes, factories, and launch facilities. Networks of floating habitats could drift with the winds or use propulsion, sails, and adjustable altitude to control their position. Cloud cities are possible on gas giants too, but more difficult. Jupiter and Saturn are already made mostly of hydrogen and helium, leaving almost nothing lighter to fill a conventional balloon. Hot, pure hydrogen offers some lift, as might vacuum balloons made from sufficiently light and rigid materials, but active aerodynamic lift or continuous powered flight may be more practical, especially as such habitats often imply fusion economies, meaning you have fusion reactors to power your engines. We have episodes deep diving the options, but bigger is better in this case, as the Q-square law makes floating cities more viable. Fundamentally, such cities would resemble enormous aircraft, buoyant wings, or fleets of connected aerostats rather than conventional balloons. There is another solution. Do not float the city at all. Hang it from orbit. A Chandelier city, discussed in our episode Colonizing Neptune, would descend from a vast orbital ring circling the planet. Towers, habitats, elevators, and industrial platforms would hang downward on immense cables, looking like chandeliers suspended from the ring above. We usually imagine buildings standing because of compression holding them up, but tensile strength is just as real. A tower can hang downward as readily as it can rise upward, provided its cable and support structure can carry the load. Structurally, it is just as safe as a tower, dropping rather than collapsing if critically damaged. We have far more time to evacuate people. The orbital ring could hold the city at whatever atmospheric level offered the preferred pressure, temperature, and wind conditions. Individual branches might reach deeper for mining, atmospheric scooping, energy, or scientific work, while inhabited districts remained higher in calmer and more comfortable layers. Elevators running up the tethers could connect the city directly to orbital spaceports, power stations, shipyards, and habitats. This makes Chandelier cities especially useful on Saturn, Uranus, Neptune, or thick atmosphere super-Earths, where buoyancy is difficult and there is no convenient solid surface, but where gravity is still livably low. They could even be built over Venus, Earth, or an airless moon, though on those worlds, simpler alternatives might be cheaper. Cloud cities treat an atmosphere as an ocean in which settlements float. Chandelier cities treat it as an abyss into which civilizations can descend from orbit. Either way, a planet no longer needs solid ground to offer useful living space. At some point, we're going to run out of living room. So how can we use celestial circular innovation to put humanity's lack of real estate in the rearview mirror? Today we'll be looking at the Banks Orbital, an immense megastructure in the form of a ring-shaped habitat more than 1 million miles in diameter, and depending on the ring's width, containing hundreds, if not thousands of Earth's worth of living area, all enjoying more naturally Earth-like conditions than any other rotating habitat design. We were talking about assembling a structure that makes all of humanity's combined constructions to date look like a toddler's sandcastle. We'll be deep diving this structure, its engineering, why it's desirable, and what life on it might be like. So let's jump into the cosmic deep end and find out just what it takes to live in space's answer to luxury living, spiced with a touch of celestial extravagance. Rotating habitat megastructures have a lot going for them. They let you pick your gravity and pressure and use way less material than a planet does for creating a given amount of living space. And since they are spin gravity environments, not mass generated, it's very easy for spaceships to come to and from. Unfortunately, the problem we have with our 3 classic rotating habitats, the Byrne Sphere, O'Neill Cylinder, and Stanford Torus, is that they are generally in the size range of a large town or county, not a planet. And for the Byrne Sphere and O'Neill Cylinder, when you look up to the sky, you see the other side of that interior, more landscape. Imagine living in a place where the sky isn't filled with stars, but more real estate. It's the ultimate in not being able to escape the neighbors. The Stanford Torus is a lot skinnier, so you see a big ring in that sky, but also a big glass dome above. They often have to use either big mirrors or glass panes to let in natural sunlight, or create it artificially. These are hardly fatal flaws, especially compared to conditions on most other planets even when heavily terraformed, but they are not ideal either. Larry Niven's Ringworld seeks to get around this by building an enormous ring around a star as wide as Earth's orbit, but besides requiring materials stronger than anything we could plausibly imagine, you still have to put big sunshades orbiting between the ring and your star to block light to give day and night, and while it contains 1 million planets with a living area, it is a pretty big lift to build. Ian M. Banks' Orbitals from his Cultural series, also sometimes called God's Bracelet for their shape and magnitude, seek to split the difference in size while also allowing very natural lighting, and we have tricks that would let us build them out of known materials without requiring super strong tensile materials, though at the cost of a lot more mass. Graphene, our go-to for continent-class habitats, has such a strong tensile strength that it lets us build habitats like the Bishop Ring or McKendree Cylinder that are orders of magnitude larger than the O'Neill Cylinder or Stanford Torus, but still are smaller than a planet. So better, but still not there. The Bishop Ring lets in natural sunlight, but also needs hugely tall rim walls to keep the air in compared to its size, since the altitude of your atmosphere is the same on them as on Ringworlds millions of times bigger in area. They also spin around a lot faster than once a day to keep gravity at Earth normal of 1G, so you can't really use the natural sunlight and have to go for a rotating hub mirror, or fake sun. The Banks Orbital, however, can rotate once a day. For any given planet and day length, there is a unique diameter for a rotating habitat that allows you to mimic its gravity while rotating its own day length. For Earth gravity and a 24-hour day, that is a radius of 1.84 million kilometers or 1.15 million miles. Size really does matter when it comes to playing Earth. That's a big number, so let me put that in perspective. That's over 2.5 times the radius of the Sun, which is the largest body in the solar system by far. So while the Banks Orbital still needs a rim wall, even a rim wall 1,000 miles high that leaks less air than Earth itself does would be minuscule in comparison to the ring's size. For Martian gravity, which has about the same day length as Earth, that radius drops to about the radius of the Sun. It will be even lower for the Moon, but because its day is a month long, that radius jumps up to 267 million kilometers, or something bigger than the orbit of Mars around the Sun. The longer the day, the wider your ring needs to be, the higher the gravity, the faster it needs to spin. And the wider and faster both add to the strength requirements a ring needs to avoid being ripped apart by its own spin and angular momentum. Tensile strength is the bedrock of rotating habitats, literally, and nothing we know of has the material strength for an Earth-like Banks Orbital. We're in the realm of needing something so strong it makes graphene look like overcooked spaghetti, and that's saying something. However, as we discussed in our episode on Ringworlds and continent-class habitats, we can cheat around this by building a second and more massive outer ring. that our inner ring can spin inside and, like a maglev train, move over it very quickly by pushing off it without touching. That outer ring needs to be strong as well, and the more massive you make it, the less strong it needs to be. One of the neat things about rotating habitats is you can get some free launch speed or slow down by landing on the spinning hull, which is a lot trickier if you have a non-rotating outer sheath like this. As channel regulars know, I am of the opinion that rotating habitats will usually be a drum nested inside a larger superstructure that either doesn't rotate or counter-rotates with the same angular momentum but more mass and less speed. So for me, this outer ring is already a normal feature of any rotating habitat. Incidentally, unless stated otherwise, for the rest of the video when I say a Banks orbital, I mean one that emulates Earth's day length and gravity. It is our default condition, though of course if you're hunting for alien megastructures, you would want to widen that range, as their planet probably doesn't match our gravity and day length. So too, since it's easier to build a lower gravity habitat or one with a shorter day, we shouldn't rule out people building them with lower gravity, though while I could see folks going for a longer day, I can't see them opting for a shorter one very often. As a reminder, our Banks orbital is 1.85 million kilometers or 1.15 million miles in radius. If you resurrected the fastest commercial plane ever, the Concorde, with its 1350 mph, greater than twice the speed of sound cruising speed, and circumnavigated the ring with in-air refueling and no stops, it would take you over 7 months to get back where you started. In short, don't expect to get anywhere fast without current modes of transportation. For every 43.8 kilometers or 27.2 miles that orbital is wide, you gain an Earth's worth of surface area. So in contrast to the Concorde example, for an orbital with the same surface area as Earth, you could just about fit the Large Hadron Collider in CERN, Switzerland, that discovered the Higgs boson particle into that 27 miles of width. Or for you fitness bunnies, if we had a Banks orbital with the same surface area as Earth, you could just squeeze in a marathon race across its width. Needless to say, I think you would build them a lot wider. This structure would orbit about as far away as Earth does from our Sun, depending on the brightness of its star and how warm you want your orbital. None of that needs to be tundra or desert, as it is a flat ring, not a curved planet with an axial tilt. You can actually tilt the rings to give them seasonal variation, but the whole of the ring will be in the same season at a time, which would play havoc with seasonally migrating species we house for an Earth-like world with seasons. It also doesn't technically have seasonal variation in day length, but the rim walls cast longer shadows in the winter, making it less bright. This will confuse the daylights out of plant and wildlife that rely on seasonal day-night length variation. Incidentally, there will be 2 summer-winter cycles per rotation around the star, adding further consternation. Though if you are as good at genetic engineering as you are mega engineering, this is probably easily fixed. The orbital lies mostly flat on its orbital plane, also called the ecliptic. The portion of the orbital currently close to the star, if it is wide enough in its night phase, will block light to the other side, usually getting daytime. This plunges the whole orbital's inner surface into eternal night. The opposite extreme also causes complete night. This happens when the orbital is oriented perpendicular to the ecliptic and its axis is facing the star. In this case, the rim walls temporarily block light from reaching the inner surface. Conservation of momentum in conjunction with the rim walls gives the orbitals its seasons. Unlike our moon, which is tidally locked to always present the same face to Earth, the orbital won't be tidally locked to the star and actually faces the same direction, irrespective of its motion around the star. We have an analog of this behavior in our very own solar system. The planets rotate about their axes roughly perpendicular to the ecliptic plane, though like most families, there is one individual that doesn't follow the norm. And with planets, Uranus is our black sheep. It's actually cocked to have its axis lie almost on the ecliptic plane and isn't tidally locked to the Sun. If we track the orbit of Uranus and imagine a ring spinning there instead of a planet, you can imagine how the seasons would play out by how the star's light hits the ring's inner surface and how the rim walls would block some of that light, casting shadow when the ring's axis gets closer to pointing directly at the star. If you were standing on the inner surface of the orbital, the star would rise on one side of the orbital half the year and rise on the opposite side for the other half of the year. Much like in the extreme northern or southern latitudes on Earth during the coldest months, the star at midday wouldn't be directly overhead and would hug the rim walls, the walls casting longer shadows over the inner surface landscape and not permitting them to heat up as much compared to when the star reaches zenith in the summer. How much the ring is tilted controls how severe this is. So while the orbital uses natural sunlight, has the same day-night cycle, gravity, atmosphere, and can be given seasons, it shouldn't be thought of as perfectly matching the conditions on Earth. We can fix the doubling up of seasons per year if we use a different star system, and I'll get to that in a bit, but the lack of a consistent direction for sunrise and sunset, the constant daytime irrespective of the season, and the lack of tides isn't going to play nice with animals and plants that rely on those things. Setting up working ecosystems will be a challenge without genetic engineering or careful selection of species. Things also get wildly different from Earth when we think about orbital velocities. The orbital rotates every 24 hours, and does so at a tangential speed of 301,000 miles per hour, or 0.045% of light speed, a very respectable interplanetary velocity. This would be sufficient for interstellar travel, albeit it would take just under 10,000 years to get to Alpha Centauri this way, so it provides a nice boost to or down from interplanetary velocities, and also ironically means that if you're patient and mining other solar systems for materials, you could sling them by mass driver to the system you want to broaden an existing orbital in and not need to slow them down, just tweaking the final trajectory and speed so it meets the orbital's inner surface at exactly the same relative speed. We'll get to how much material we need to build one in a bit, but let's talk about width. As mentioned, this thing is a couple of million miles wide in diameter, and every 27 miles of width in that band adds another Earth's worth of surface area. So you can get 2 eclipses a year, but only if the orbital is wide enough. Imagine having your day interrupted by a scheduled mini eclipse, courtesy of your local orbital configuration. It's the new daylight saving time. You need an orbital in the order of 800 Earths worth of surface area to actually get a full eclipse. That's a band 35,000 kilometers or 22,000 miles wide for the specific case of our Sun and our orbital distance. So one this wide does have to be tilted to get sunlight too, and you might use minimal tilting and wide bands to moderate light if you really wanted a 365-day year, but that would be a bit closer to the local star than comfortable in terms of lighting. There's a lot of options. Incidentally, I'm borrowing heavily from the Encyclopedia Galactica entry on Banks orbitals over at Orion's Arm, written principally by Stephen Innes, and since our calculations keep matching, I'm going to trust his going forward and save some time. One thing that gets mentioned in there that I don't recall noticing before is that when you tilt the ring, you create 2 warm seasons per year. For this reason, you could get away with a wide orbit too, to make a longer year if you want to avoid a double set of seasons per orbit. Another way to get seasons is to use an elliptical orbit, which will make it winter when the orbital is further away from the star and summer when it's closer to the star. You can also combine the 2 effects. If you thought deciding where to install and how to tilt your satellite dish was tricky, try choosing an orbit and tilting a megastructure for optimal seasonal variation. If the season variation is too quick for your preferences, a slightly brighter star than our G2 yellow sun might be preferable, such as a G1 or G0 or even an F8 or F9, as these are only a touch more massive than our sun, but a good deal brighter, so their habitable zone distance has a longer year, and again the lack of spherical curvature on these rings, like planets have, mean they are going to be warmer overall than planets at the same distance. You can also still use shades or mirrors to enhance or decrease or modify the brightness and spectrum of the native star, but while a Banks orbital is quite massive, it still isn't really going to have proper Lagrange points like a planet does, so your shade or lens or mirror needs to be a laggard to keep up good pacing with the ring's own orbit around that star. You could use a similar trick to give it a moon if you wanted, but that ring is still rather bright at nighttime, as we'll get to in a bit, along with mass. See our Statites and Lagites episode for more discussion of that. As a general point, the habitable zone and year length of any star is based on its brightness and mass, but brightness rises at a bit over the cube of mass, while orbital period drops with the inverse square root of mass, so habitable planets around red dwarfs have periods of weeks or months, while big giant stars can have habitable zone periods of centuries. That is for main sequence stars. I should also note that a subgiant star on its way to red giant is brighter for the same mass, and thus might also be popular places to stick such rings. The timeline for subgiant phases for stars like ours tends to be on an order of 1 billion years, so you can easily migrate or increase your sun shields as it slowly brightens. those L1 sun-altering effects are not altering that star to look unlike a normal sun, even ignoring that we do not look at the sun directly, which appears quite white if you do, not yellow. You would not really see a swarm of satellites there altering the content of the light coming through. And of course, if you can build things, you can also migrate them. Should you decide your star is nearing its end, nothing stops you from artificially lighting one of these for a trip, and you could build your engine on the back side to serve as your fake sun for the trip, flipping it around for the slowdown. Should your star start showing its age, just pack up your several trillion square kilometers of living space and move. It's just like moving a house, but with a slightly bigger van. Of course, they take a lot of energy to move, and we should discuss mass. We usually hold that at a bare minimum, you need a meter of thickness under you, or at least 1 ton of material for every square meter of artificial land under your feet, and many would prefer something closer to a kilometer of landscape and hull under you at more than 1,000 times that mass. For Earth, that ratio is several thousand kilometers and about 12 million tons per square meter. That means your mass per unit of living area for rotating habitats is normally anywhere from 10 million times as good as Earth to maybe 10,000 times. We tend to assume that bigger continent and planet-scale habitats go a lot thicker on their landscaping too, even if they are dimpling their hull for deeper or taller lakes or mountains and filling the latter with aerogel to cut down on mass. In the absence of something like mag matter that makes graphene seem like weak, warm butter, we have to use that thicker outer ring approach. That might be a giant torus, flattened on one side for the ring to sit inside, and the rest covered in solar panels and ancillary facilities. It might just be full of compressed hydrogen and helium gas too, like a donut-shaped brown dwarf, given their abundance and limited usefulness for construction. If you have a fusion economy that can actually use hydrogen or helium as your fuels, then it's a good way to store your reserves, and if not, if you can't do better than deuterium fusion, then it gives us something useful to do with that material. If we just for the moment imagine disassembling Jupiter to make such a ring from, and one of about 1,000 Earth's worth of living area, you should have no problem getting all the material from Jupiter's core to build a mile-deep landscape, and still have tons left over for that outer ring. Disassembling Jupiter from material might just upset a few folks, but think of the real estate opportunities. Always look on the bright side of planetary destruction. Of course, for some of us, planetary destruction is the bright side too. Indeed, you should have enough material for several of these killer Earth-scale Banks orbitals, and you can always import from other star systems with less desirable locations or spectrums, if you need more material or want to leave Jupiter alone for sentimental reasons. A solar system like ours should have the raw materials for a couple hundred of them in this size range, or 1,000 the smaller variety of just 200 Earth's worth that is referenced in Banks' novels discussing orbitals, and that's before resource extraction options like starlifting or importing matter from neighboring systems with less desirable stars. Field trips in a Banks orbital will be epic. Today's lesson, orbital mechanics, followed by a practical demonstration. Tomorrow, how not to get lost on a megastructure. Essential survival skills. You could in fact set these up like chain links, with each habitat on the same orbit of its sun having a neighbor spinning through its middle with its seasonal angle cocked in the opposite direction. Usually when I refer to chain link worlds, I'm talking hoop worlds, donut-shaped artificial planets that are full of mass for gravity, but this is probably the easier version. Now I said temperature is the same everywhere, but that's not quite true and doesn't imply similar weather either. As an example, my home is at 42 degrees latitude and is in the northeast corner of Ohio, and is the same latitude as Rome in Italy. My area has only slightly more mild winters than Buffalo, New York, my home away from home, which is at 43 degrees and legendary for its snowy winters. Paris, France is way further north, 48 degrees, more than most of Canada's population, and London almost 52 degrees. Your landscape controls your weather and temperature a lot, and we can build those as we please on such artificial worlds. But not every place gets a 12-hour day all year either. Those rim walls are enormous structures hundreds of miles high, potentially even 1,000. We usually imagine stylizing them as impossibly tall mountains, and on smaller habitats they would even have significantly lower gravity as you got higher. But on a Banks orbital, even a 1,000-mile high wall is tiny compared to the radius under rotation, so gravity would barely diminish. In theory, they could be made of a clear material, but given the necessary thickness, I think even something translucent would be dubious. Indeed, you'd likely nest the ring and its entire rim wall in your outer torus for added protection, and that means you have shorter days near the rims. How much this affects the habitat as a whole depends on the width of your bracelet or axial length. Again, every 44 kilometers or 27 miles of this axial length is giving you another Earth of living area. But half your time, your area near a rim wall is under partial shadow, and how much just depends on the rim wall height and your tilt. If your habitat is much wider than your rim walls are tall, the effect is fairly minimal outside those areas, and the same if your axial tilt of the ecliptic is fairly minimal. The sharper the tilt, the more seasonal habitation habitat-wide, and the more shadow by that rim wall, and this will also help drive weather, especially as you might decide you don't want a flat ring, but one with a little curvature, either bowing up in the middle or down in the middle. Up in the middle means water will tend to drain toward the rim walls, down toward the middle, and you could get away with shorter rim walls if you had enough drop toward the center. Any mountain ranges you place throughout the habitat are going to locally cool things too, and these can help drive weather and break up storms, but there is no Coriolis effect and major temperature gradients driving the more vicious cyclonic weather we see on Earth, let alone places like Jupiter, which is much more massive than one of these rings but considerably smaller, though the axial tilt can allow some monsoon-like effects. You can also place them on a more elliptical orbit rather than something circular, so you can get your twice-a-year season from the tilt overlapping with your high eccentricity season caused by getting further and closer from the Sun, with a summer effect when it's closest or at perihelion. In this way, you get a high summer effect by timing one of the two axial summers with the perihelion summer, and your aphelion winter would be the same time as your other summer, making it a lot more mild, or even still wintry if you're using a rather eccentric elliptical orbit. In the absence of a moon of real mass, which would probably be a pain in the neck, you do not get lunar tides. We're missing out on those romantic moonlight nights and werewolf stories, but on the bright side, no high tide means no unexpected swimming sessions. If you want a moon, you could fake one with Ligites or orbit some hollow moon around the bank's orbital, though I would not trust that moon option unless you were using the supermassive outer sheath secondary ring to add a lot of mass. You do still get solar tides though, and pretty impressive ones, as you are getting 2 million miles or 3 million kilometers closer and further from your sun every day as that bracelet spins. That's a 2% change in distance for an even spot of that ring relative to its sun every day, or a 4% change in its gravity on you, and that would parallel ocean tides here on Earth, though you might want to use smaller basins akin to seas or Great Lakes, which would reduce that. Those near dimmer stars will have worse tides, and those on eccentric orbits will have tides varying over the year as they get closer and further from the sun. Now, the one thing you probably don't have on these is a moon, and that's because they are wider than all moons' orbits, and unlike a sphere, a big ring is not exactly ideal for orbiting around stably. Again, you could fake one with a Ligite, and would appear exactly like our own moon if you liked. But that ring is quite bright at nighttime too. Our moon, when full, has a solid angle of about 65 microsteradians, about the same as our sun has, and the Earth from the moon is about 14 times bigger, at 880 microsteradians, and would be about 14 times brighter in the sky on the moon than the moon is here, adjusted for different albedo or reflectivity. A Banks orbital is further away, so that a given moon or Earth-sized object would be reflecting on a 24th as much moonlight, or ring light, on its night side when getting sun, but that still means even a relatively thin ring of only a handful of Earth's living area is much brighter than our full moon, like some big bridge across the sky. Who needs constellations when you got the ultimate nightlight? And very visible with its landmasses too. To the naked eye, with 2 layers of atmosphere in the way, it probably looks like a blue, green, and white smear, but even simple binoculars will let you identify bigger seas and landmasses readily enough, especially directly overhead where light passes through the least air both ways. You might be able to make out seas and continents with the naked eye too. You don't see it curving away either. The curvature is 100 times less than on Earth, and turns up rather than down, but should smear off into a red haze, then re-emerge as a red hazy ring slowly turning blue and green as you look higher, when looking in the ring direction, which we'll call east and west, North and south are toward the rim walls, and by default we assume this is flat, other than landscaping changes, but I do think you would put a slope in to make the middle or equator slightly lower, which would result in a thin ocean belt around the whole ring, sort of like we discussed in Topopolis, the Eternal River, in our February Nebula exclusive. That structure is the exact opposite of the bank's orbital too, very skinny radius and incredibly long axial width, so it looks like a thread, not a ring. Don't think of the ring as being ruinously bright either. Folks tend to forget our eyeballs are logarithmic. The sun at noon is 400,000 times brighter than the full moon, so even a wider ring that might be 1,000 times brighter than the full moon is still darker than twilight or very overcast days. You do have options for handling that too, like having a nested ring inside made of panels that flipped out of the way for sunlight, turning perpendicular, but then rotated in to block ring light at night. I personally don't think you'd bother, given it wouldn't be as bright as many suburbs at nighttime, much less cities, but you might. Speaking of nested rings, in addition to the chain link connection of the orbital, which I'll dub a Banks chain link world, which could be through the middle or even close enough to touch atmospheres, which might be a neat effect, you could nest some smaller rings inside the orbital cocked at higher angles to give an appearance of an orrery of 3 or 4 of these together, maybe more. And of course you have countless additional facilities and smaller habitats in and around one too, adding themselves as constellations in the sky. Those cockeyed ones, which I will name a Banks orrery, could get away with being just say 10,000 kilometers smaller in radius for each one, with just 0.5% drop in gravity in order to maintain the same day length of that shorter radius. The rings would shadow each other a bit, but create far more connected living area, and direct physical connections would be possible using the same sorts of tricks we discussed in the Megastructural Compendium for devices like space towers or skyhooks. You'd rotate under each one once a day for an extra eclipse, so you wouldn't have more than a few unless you want to have your Banks orrery a bit closer to its star, but it would still be pretty minimal. You are spinning 300,000 miles per hour, so crossing under a higher ring, even 20,000 miles wide, is only eclipsing things for 4 minutes at a time. This episode should air about a month after the big annular eclipse a lot of North America is in, including my house, so for those experiencing it, you will recall that it's not really dark during an eclipse, just dimmer, more like a very thick cloud passed in front of the sun on a partially cloudy day. Amusingly, you could chain link these Banks orreries together too, a Banks chain orrery I suppose, and if you're chaining these, you could also do nested rings of them around that sun, just as we sometimes contemplate doing with Ringworlds or Rungworlds to form a partial Dyson sphere. There are some fascinating variations of these structures over at Orion's Arm, and some short stories and fiction set there. Orion's Arm is a shared open-source hard sci-fi setting, and its Encyclopedia Galactica has always been a favorite resource of mine long before I started the channel, and many articles also cite me or were contributed to by me, so odds are if you like the show you'll enjoy that site. The same goes for Ian M. Banks' excellent Cultural series, which is generally pretty upbeat and optimistic, and where the Banks Orbital is just one of several giant megastructures we get to explore, and Banks was a great storyteller. The orbitals in there are their alternative to settling planets, as they just build those orbitals to live on as more mass efficient and customizable. Now that we've explored them in theory and fiction, will we ever see them become a reality? Hard to say. I think if no other engineering barriers pop up, which is probably optimistic, we will at least see some built to prove it can be done, maybe even as soon as in a few millennia, but I'm a little less optimistic about them becoming the mainstay of civilization as they are in the cultural novels. In a few millennia, if we have not found something shinier to distract us, we might just build one, or we'll get halfway and decide to make a great tourist attraction as the galaxy's largest unfinished project. Either way, it's a win. Their size makes them a big investment and an interconnected one, whereas you can build O'Neill cylinders and smaller habitats, still able to house many thousands, connect them by tethers and shuttles if you like, and still be able to pack one up and leave, since they are very easily modified to be spaceships. So I think it is easier for me to see a billion O'Neill cylinders being built and parked next to each other, connected by tethers, than a Banks orbital, and both have similar total living area. Besides, we have bigger versions of these in the forms of the Bishop rings and McKendree cylinders that can allow a potentially happy medium. That said, powerful people like to leave behind imposing monuments. You only need to look at the pyramids to understand how that works. So if you're an all-powerful, ostentatious ruler, or community wanting to leave your mark on history, you could do worse than creating a bank's orbital legacy that 1 trillion people can live on with tons of elbow room. For more altruistic pursuits, we could produce continuous ecosystems bigger than a planet to house all those wonderful species that were snuffed out through natural calamities or human encroachment. So I think there's a future for Bank's orbitals, and a beautiful future at that. How could it be otherwise in a solar system decorated with God's bracelets? Ribbon Worlds. The Bank's orbital is an immense ring habitat, and later will go bigger still with Ringworlds. Yet both designs run the same basic obstacle: tensile strength. The faster a ring spins, the harder every part of it pulls away from every other part, like a suspension bridge whose roadway continues all the way around in a circle. For an Earth-like habitat, we normally assume that spin must produce 1 full Earth gravity, and that places a hard limit on how wide a ring made from any given material can become. But 1 Earth gravity is a preference, not a law. A ribbon world is a ring or cylinder habitat designed around the minimum gravity its purpose actually requires. If plants, machinery, or genetically adapted inhabitants function comfortably at 1/10 gravity, the ring can be 10 times wider without increasing the required rim speed or tensile stress. Go lower still, and the ribbon can stretch to truly planetary or even interplanetary scales, using materials that would never support a Banks orbital at 1G. These might serve as enormous orbital farms, industrial zones, spaceports, or low-gravity parks. Given that plants seem to do fine in low gravity, so long as there's at least some gravity for them to line up and down on, this might be the normal setup for farm habitats. Smaller, conventional habitats could hang from them like beads on a bracelet, providing Earth-like gravity for homes and offices, while the ribbon itself supplies farmland, transportation, storage, and launch infrastructure. A civilization adapted to low gravity might simply use the ribbon as its primary living environment, making the largest ring habitats not Earth-like worlds at all, but nearly weightless bands encircling planets or whole planetary systems. And often, low gravity is much preferable to no gravity. There is also a related trick that turns the usual ring habitat inside out. Place a ring around a massive planet, star, or black hole, and let people live on its outer surface, with their feet pointing inward toward the central mass, like here on Earth. Natural gravity now supplies down, while the ring's rotation produces centrifugal force in the opposite direction. By adjusting its speed, you can cancel part, but not all, of the central body's gravity, turning a crushing environment into a comfortable one. A world with 3 times Earth's gravity might support a ring where rotation subtracts 2 Gs, leaving the inhabitants with 1. Unlike a free-floating spin habitat, such a ring may need active support or enormous compressive strengths to keep it from falling inward, especially if it rotates below orbital velocity. But it lets us treat gravity not merely as something to generate, but something to subtract and tailor. And once we start using massive worlds as structural components, rather than merely places to live, is a small conceptual step from rings around planets to entire artificial shells built over them. Earth is immense, but we only live on a thin shell of its surface. So what if we built a planet with only that thin shell, or with several layers of them? So today we'll be discussing why and how you would build hollow planets, what we often call shell worlds, as well as multi-layer concentric designs, the Matryoshka shell world, and we'll also touch on hollow moons and hollow suns. I want to emphasize that much like when we discussed building flat Earth megastructures, these are serious designs with a lot of logic behind them, for man-made planets humanity might one day build, or which other civilizations that might exist elsewhere in the universe might have built. We are not really interested in conspiracy theories claiming our own planet might be a hollow Earth, but as we'll see today, you could build a hollow planet that would convincingly fool even modern science into thinking it wasn't hollow when it actually was. So we can't exactly say hollow Earth is debunked, especially since, as we'll also see today, there is very good motivation to construct hollow planets and shells as opposed to classically terraforming Earth-like planets. We probably should start by noting that there is no single unified Hollow Earth theory, as it describes a lot of theories ranging from the scientifically coherent to pseudoscientific to simply fun plot devices for fictional stories. Those last are equally important to us because when you are in the mega engineering game, you build to what people want as much as to what is practical. So if people want a firmament that is shot through with massive caverns and underground ecosystems, like the Underdark common in various D&D settings like the Forgotten Realms, then you build them a firmament that looks like a Swiss cheese with extra large holes. And this is one common approach to Hollow Earth, merely that the upper layer has a lot more underworld space than our own planet. Indeed, this is a scenario many planets might have, not just from naturally occurring lava tubes, but as a byproduct of a civilization mining its surface for many millennia, or even some larger species that acts like ants and burrows immense caverns akin to scaled-up ant hives. One of our recurring points today will be that hollow space saves mass. This is especially true in regard to the mass of valuable elements used for construction like carbon, aluminum, or iron, as opposed to hydrogen or helium. Thus, a lot of artificial planets, be they shell worlds or rotating habitats, probably do go heavy on hollow underworld layers with lots of caverns filled with mushroom forests and underground lakes, because it saves valuable mass while adding an interesting feature for residents or visitors. Of course, in most versions, it is not simply far more caverns with lost world civilizations inside them. It's entire extra layers of planet, sometimes even with their own lighting. Imagine, if you will, a world beneath our feet that is not composed of molten lava and a fiery core, but of vast unexplored caverns, mysterious landscapes, and possibly even civilizations thriving under the radar, quite literally. The main Hollow Earth theory has its roots in the imaginations and speculations of thinkers and writers through the ages, from Edmund Halley himself, for whom the comet is named, proposing in the late 17th century that Earth might consist of several concentric shells, to John Cleves Symmes Jr. in the early 19th century, who famously declared the Earth to be hollow and habitable within, inviting explorers to find these entrances at the poles. Symmes' call to adventure, however, seemed to overlook the slight inconvenience of freezing temperatures and the absence of any giant openings below. We in modern times can now laugh off the notion of vast underground chambers or lakes beneath the poles, except of course for the many vast chambers and underground lakes we've found under the Antarctic ice, like Lake Vostok, the largest of Antarctica's several hundred known subglacial lakes, which is the 16th largest lake on Earth by area and the 6th largest by volume. There is life in there too, though thus far we've only found bacteria and fungi, and it isn't hard to imagine a more energy-abundant civilization might float little fake suns around in underground lakes and seed them with some photosynthetic life. Just a big floating fusion reactor with artificial lighting as its outer shell, or that an underground lake like this might have thermal vents bringing in nutrient and energy from deep underground, or that a civilization might make some or add more vents. Now, Hollow Earth itself can be a bit of a misnomer. Unlike the shell world megastructure we'll discuss in a bit, it usually is not assuming the planet is a thin shell or crust around emptiness. The exception to that are versions in which people live upside down on the inner edge of the shell, and all the heat from below that we get is not a hot molten core, but rather a sun of some sort shining up on these folks living upside down. This has the same problem a classic Dyson sphere has. There's no gravity there. The nature of gravity is such that if you live on the surface of a sphere, you feel downward gravity toward the center, and if we hollowed it out, those on the surface still feel gravity in that same direction, albeit weaker from the removed mass. But if you are inside a spherical shell of mass, then you are not only weightless at its center, as folks tend to expect, but weightless anywhere inside it. Even standing or grabbing onto the inner side of a shell, touching one side of it, still results in all the other matter pulling on you evenly, for net zero gravity. A neat side effect of this is that if we wanted to add another layer to Earth, we could build one higher up, a huge massive spherical shell more people could live on, and it would have zero effect on gravity down here on Earth's original surface, but it would generate more gravity for those living on it, and would also add its gravity to another layer above it if we built one, helping keep gravity from weakening as you went further from Earth's center. Coming back to Hollow Earth theory and its more modern incarnation, in an era of better knowledge of astronomy and geology, it is a theory that has been kept alive by science fiction writers, conspiracy theorists, and the occasional adventurous spirit wearing a tinfoil hat as a fashion statement. The allure of hidden worlds is irresistible after all. Who wouldn't want to believe in a secret utopia beneath our feet, complete with its own sun, ancient and advanced civilizations, and exotic wildlife, possibly including things we believed extinct like dinosaurs? And of course, this is part of its appeal to us when we contemplate building hollow worlds. We could go through the mainstream science, patiently explaining the plethora of evidence supporting the fact that Earth is indeed mostly solid with a molten core, but I suspect very few of our viewers are in doubt on this. Maybe we should anyway, since I don't think most folks know why we believe in a molten core or how we've proved it, but the short version is that when we have earthquakes, the seismic waves travel through the planet, and the speed they move at is based on the material they are moving through. Detecting these from different angles and distances lets us map out the interior. It also basically ruled out a hollow interior unless the folks crafting it had gone to fairly extreme efforts to mimic the surface seismic effect of a quake originating deep in the mantle and spreading out over many hundreds of miles on the surface. Though building such an artifact is an extreme effort, so we shouldn't go assuming they wouldn't include such an add-on, and they could do it. It wouldn't be that hard to have your earthquake machines on the inner side of the shell set to vibrate while synced at the right timing, frequency, and strength to full seismologists. It rather depends on how badly you want to mimic a regular planet, and how much the cost savings and benefits are to using a hollow planet over one you found and terraformed or built with regular planetary matter. So while the Hollow Earth theory enthusiasts hold on to their belief with impressive tenacity in an era where Google Earth can show you every inch of this planet's surface, we can at least recognize that the idea of vast, unexplored territories just a mole man's journey away is an undeniably appealing idea. You might not want to pack your bags for an expedition to the center of the Earth just yet, as the journey through the planet's crust might be a tad warmer and more solid than expected, but the Hollow Earth theory remains a delightful detour into the world of what-ifs and why-nots. After all, in the grand tapestry of the human imagination, who's to say there isn't room for a little hollow space? And so we see their appeal and can now ask, might we build such a thing, and if so, why? Here's the key reason, and it's a big one. We believe most of the matter in this universe is composed of dark matter, a substance whose only two known and fairly definite traits are that it generates gravity like normal, and that it doesn't interact with much of anything, meaning it's useless for building out of, but if you could trap it in the core of a fake planet, it would give you tons of free gravity, without needing to use valuable construction materials. Indeed, you need do nothing to keep it there. It interacts so weakly that every particle, once in place inside that shell by some unknown means, and at a velocity less than the escape velocity from inside it, would simply have every particle of it remain in there on 100 trillion lonely and undisturbed orbits. It is literally the ideal material for building fake planets out of, hyper-abundant and good for nothing else. Artificial black holes are next on that list of ideal gravity generators, barring some actual artificial gravity devices such as those ubiquitous in science fiction. But first, let's talk about an alternative to dark matter. After all, we barely understand the stuff. There are still many scientists who are pretty skeptical if it even exists, and we have no obvious pathway to manipulating it to gather it up into handy little planet-sized spheres. Something very prone to gathering into little planet-sized spheres is regular matter, and most of that is hydrogen and helium. Helium bonds to nothing and thus can't be used as a construction material, and while hydrogen bonds to plenty of things usefully, it is so abundant that there's not enough of everything else for it to bond to. So we can store it up in big spheres to use it for gravity and possibly one day trickle it into fusion reactors or stars themselves to extend their lifetimes, while removing their heavy elements via starlifting to provide construction material. The problem is that by default, a ton of hydrogen and helium in one spot is a gas under pressure, or fluid anyway, and only when we cram in more of it than the mass of a planet like Earth do we get enough of it packed in dense enough to offer Earth-like gravity, rather than something weak like lunar gravity. We'll get to hollow moons in a bit, but for the moment, we want an Earth-like planet. Of course, we might want something bigger than Earth too, and a shell built around Saturn just over its atmosphere would have very nearly the same gravity as Earth, with very nearly 100 times the surface area. Some folks might be wondering why this shell isn't simply falling inward, and of course channel regulars are thinking of active support methods like orbital rings and Atlas pillars, but we will return to that in a bit too. We might start by asking why the crust of our own planet doesn't simply fall into the core, and in point of fact it actually does over long enough periods of time. The continental shells are basically rafts floating on magma and are not eternal or stationary. Simple buoyancy keeps these rafts afloat. The Earth is the densest known object in the solar system, and the core the densest part of it. The mantle has a lower density of about 3.4 grams per cubic centimeter, or 3.4 times that of water, while the crust is around 2.6. We often refer to this density as specific gravity without other units, and water is one. Denser objects are higher, like the iron in our planetary core, which is 7.9. Even that's a little too simplified, as the core, mantle, and thin shell of the crust all have additional distinct regions or layers with different properties, and if we feel like engineering an artificial planet, we probably stop at one of these layers and then have to simulate the effects of the others to the degree needed or desired. But while rock, magma, and metal are a lot denser than water, compressed hydrogen and helium are not. Hydrogen at standard pressure and temperature, or STP, is 0.09, less than a tenth of water, and helium is about double hydrogen at 0.18, whereas Earth overall is 5.51, 30 times denser than helium and 60 times denser than hydrogen. So we can compress them, but now we need an airtight shell or balloon to keep them packed in, and if you puncture it, then material will go venting out. Now that's not that big a deal, especially if it's chemically inert helium, but hydrogen venting out into an oxygen-rich environment is one match away from igniting. But even here, it would be no worse than a volcano and probably gentler. The question is how thick your fake crust is to resist puncture, and anything over a kilometer isn't likely to puncture even against a nuclear strike or asteroid less than a kilometer wide. You also have means of sealing them, such as putting a patch on, and we could imagine big sturdy bubbles filled with a slightly lighter mix of gas floating inside the gas interior that would float up into a puncture and seal it too. Or just drones living on the inner surface of your shell, walking around with magnetic boots perhaps, that would go over and seal a crack. Problem is, you don't want a thick crust here either, as you are essentially making a balloon, albeit one vastly stronger than any rubber balloon. Those expand as gas pressure inside rises and stretches the balloon, which resists by elasticity. Here, the resistance is raw gravity, as that surface shell is being pulled down. So long as you are keeping it reasonably airtight, some leakage is fine, the gas pushes up and out, and the shell pushes in and down. On Earth, or a place with surface gravity akin to Earth, roughly every 10 meters of water or 4 meters of crust is adding 1 atmosphere of pressure downward. So by the time you're even 1 kilometer down, you're up to something like 250 atmospheres of pressure holding your balloon together, and that gas is pushing back at whatever pressure its density and temperature has, which is lowest up near the shell and highest in the core. Unlike a normal pressurized vessel, it's not got the pressure evenly distributed throughout. It will also depend on the temperature you keep that gas at and the actual ratio of hydrogen to helium. At a certain point, these materials will also be crushed into liquid hydrogen or helium or metallic hydrogen, And of course on the far end of this, you can ignite fusion. There will be some ideal surface depth for a given planetary radius, gas mix, and internal temperature. The extreme version of this is the Edosphere, which assumes a steel shell a third of a mile or 500 meters thick around a gas ball 37 times wider than Earth called an Edosphere, and which does have much lower gravity than Earth. The smaller you want it, the thicker or denser that crust needs to be to keep it going. This general class of artificial planet is called a bubble world, and really is not suitable for building planets that aren't a lot larger than Earth. Generally something the size of Saturn is contemplated if your goal is to have Earth-like gravity. If you want a certain crust thickness and your density isn't optimal, you can go thicker by including lots of hollow pockets, or other type of hollow Earth with a vast amount of underground caverns. You could potentially emulate magma with something cooler. Lead has a higher density and lower melting point for instance, but I generally don't think of volcanic activity as something you want to import to artificial planets. And as we discussed in giving Mars a magnetosphere, there are so many better ways to protect a planet, including with an artificial magnetosphere, than by using quadrillions of tons of molten and radioactive metal. These shells are also a great way to make storage for hydrogen and helium you want to later use for fusion or refueling a star. And as an example, a bubble world of Saturn's mass, with 100 times the living area of Earth, could store 25 million years of fusion fuel for our Sun. You could stick 100 of these in an orbital circle around our Sun out where Earth is, and this is called a Kepler-Rosette orbit and is reasonably stable, and in the process get 10,000 Earths worth of living area, all while storing your fuel to keep that star running for another 2.5 billion years. And you can, via star lifting, keep your star going indefinitely by pulling out the helium from your star to fill such hollow worlds and inputting new hydrogen from your planetary tanks. See our episode Refueling the Sun for details. Speaking of suns, you can also decrease the wavelength of any star or stellar remnant by building a sphere around it of tungsten or some other alloy that melts at a temperature similar to our own sun's surface. You place it at a wider distance where the total radiation coming off that star, white dwarf, neutron star, or black hole would be absorbed and re-emitted at that lower temperature and peak wavelength. Hollow stars like this allow you to adjust the spectrum of hotter stars to the color or temperature we prefer, and avoid the huge amounts of ultraviolet or even X-rays and gamma they might give off. This method can also be used to handle stars that are less stable in their output, as a thicker shell will absorb energy over time but emit it as a more stable black body emission. This can also contain coronal mass ejections and solar flares. You can also use this technique with smaller or cooler stars, by making the polar regions of the outer shell reflective and the equatorial band the planets orbit in clear, or again of tungsten if you need to bring the temperature down again or normalize the spectrum and output. We call this star boosting, and it is a way to adjust cooler stars to produce a hotter spectrum and more strongly in the disk their planets orbit in, widening its habitable zone. Shells like this don't necessarily need to be very thick or have any active support. See our episode on statites and ligites for the mechanics, but they should be able to float by radiant pressure holding them against the gravity. Now on the smaller size, getting back to the shells held up by internal gas pressure pushing back against a more modest gravity. These are often called gravity balloons, and we contemplate them for asteroids, where we expand an asteroid into a thin, hollow shell and fill it with either a breathable gas mix or some thinner mix of hydrogen and helium. Here the purpose is just to keep the gas in and give it a protective shell of matter against micrometeors, accidents, or attacks. And your gravity is either very minimal or generated by rotating habitats floating around inside the gravity balloon. They might maintain position by using thin air sails or by simply being tethered in place. Such structures have a lot of options for internal use. One other variation of this is the hydro shell, where the balloon layer is covered in water to allow very deep oceans, but at much lower pressures than such depths usually would have. We discussed those in our episode on marine space habitats, And we noted there with enough water, you don't even need a filling for the shell, especially as we don't want tons of gravity. But in that case you do need active support to keep the shell going. However, these are a nice pick for hydrogen and helium filled shells, since they are naturally lower density, benefits us in keeping lower gravity and lower pressure in those oceans above the shell. The hydrogen could then trickle feed large fusion reactors on the shell, powering long vertical lighting towers for the ocean and pumps to churn nutrient and air through the water. An example of what I like to call vertical reefs. This low gravity issue from a gas filling of the shell will generally be true of any other hollow Earth designs we discuss, though there are some specific options for using a dim red dwarf or even a white dwarf with a very careful balance to avoid a nova to keep your gas hot and at higher pressure, while providing an equivalent to geothermal heating. You might want a lot of geothermal heating too, as you might not be planning on lighting this artificial planet conventionally by orbiting it in the Goldilocks zone of the star. As we discussed in colonizing white dwarfs, you can build large, wide ring-shaped bands around a white dwarf or gas giant as an alternative to this balloon approach. And you can also build a large, actively supported spherical shell that holds itself up through orbital mechanics. We've discussed it in detail in other episodes like orbital rings or space towers. But the abridged form of that is that if I place a small, ferromagnetic sphere, say iron, in a circular orbit around a planet, and then a bunch more, to form a loose ring, maybe even chain them together to help keep their spacing on their ring, I can now wrap that ring with a thin sheath, something magnetic that will keep it from touching them or drifting into them. Now, if that sheath is rotating with them, all is well. But we can also make it stationary to the ground below, and they'll keep spinning within it like water through a hose. But we need to spin them a bit faster in this inner ring to make up for the missing orbital momentum the outer ring or sheath is missing by being stationary. There's no complexity to this scientifically, it really is that easy, but it will leak energy unless you're using superconductors, and you need to magnetically shield it for safety, which can be tricky. But this is an orbital ring, and you can scale this up and put many next to each other to make a band you could build a big stationary hab on, or layer them up like thread on a soccer ball under the surface patches to build a rigid sphere you can live on. The cousin to this is the Atlas pillar, which simply runs this sort of matter chain up a long vertical pillar and back down again, and holds a platform on top by the same mechanics a piece of paper would use to float atop a heat vent, or if we blasted the underside of something with a water hose to hold it up. By encasing such a device inside a closed loop, which might need some power added to handle slow heat loss, you have a structural pillar that can hold weight up better than any known substance. We deep dive these more in other megastructure episodes, so we'll leave it there for the moment. And their value to us is that they let us make a hollow sphere at whatever distance from a chunk of mass we like. Once planets get bigger than Saturn in mass, they don't really get much bigger. Jupiter is only about 10% wider than Saturn. Indeed, as we add mass, they will stay about Jupiter sized, all the way up through brown dwarf levels up to red dwarf size, at about 25,000 times the mass. The gravity on the surface of a shell right around this would be murderously high, 250 times that on Earth, so if we want Earth gravity, we would need it to be wider, indeed wide enough to have 25,000 times Earth's own surface area, or the square root of that, about 150 times wider than Earth. Needless to say, that leaves us a huge empty volume around that brown dwarf. You can't rotate a planet that big on a 24-hour day without having vastly lower gravity at the equator from the centrifugal force, meaning you either need to make it more egg-shaped, or live with the lower gravity there, or just put a fake sun around it that orbits your mega-Earth geocentrically, or possibly a Kepler rosette of several of them. We played with variations of that more in our episode Mega-Earths. This is how shell worlds work. Your gravity goes down inverse square to force, so to maintain the same surface gravity, you need to increase your mass with the square of your sphere's radius, which is also what your surface area rises with. Thus, any Earth-equal body, when it comes to gravity, has the same mass to surface area ratio Earth has, 100 times the mass, 100 times the living room, 100th the mass, 100th the living room, or living area. Living room can be increased on any of these by adding in hollow pockets throughout your shell, like those versions of the Underdark or Hollow Earth, and you could light them. You can also add concentric shells, and these don't need much more mass, just enough to compensate for the extra radius. If your next shell is 1% further out, then gravity will have dropped to 98% of normal, and you need that shell to have about 2% of the mass of the body below it to keep the gravity the same. You can keep adding layers indefinitely, but if you're lighting them you will have heat dissipation issues. We discussed options for that in Matryoshka's Shell Worlds, including potentially transforming Earth into such a world, or even scaling us up slowly through more and more layers into a Birch Planet, an enormous construct with a mass closer to that of a galaxy than a star, let alone a planet. You also need power for these things, which is where building them around a dim red dwarf or a cooler white dwarf often comes into consideration. But those are huge, and as we've noted elsewhere, we can also build them around even bigger neutron stars or black holes, which are vastly better power sources. The neat thing about black holes, though, is that while they only form naturally from stellar remnants about 1,000,000 times more massive than Earth, we believe we can make them artificially a lot smaller than that, and under current theory they could exist even at masses much less than Earth. This allows hollow Earths much smaller than our planet, such as asteroids or moon-sized ones, as you can fill that black hole up on cheap hydrogen, helium, or dark matter to the desired mass and then trickle in more to keep the active support powered and provide any power needs you have. Black holes make awesome fake suns too, especially if you cram one into something the size of a small moon made of a tungsten shell and fill it with gas of the right density that the black hole will absorb just enough to release energy to keep that gas hot and high pressured, and heat that tungsten sphere to just under melting temperatures to make a nice fake sun that you can orbit your giant fake planet with. There's also no pressure and drag issues inside these planet shells, unless you're making an artificial sun from it, with a black hole in the middle, so you can build lots of layers or even fill the interior with a swarm of rotating habitats orbiting the black hole, or more strip worlds or bracelet worlds that ring the black hole. These type of ring worlds need not be evenly distributed either. You can make them wider at certain places to be more like an orbital plate, which is basically where you hang an artificial continent over a planet that's held up by orbital rings that extend thinly beyond it or atlas pillars. You could also make a ring just a bit smaller in radius than your shell that's spun inside it, offering centrifugal force as gravity but upside down, like we imagine for classic hollow Earths. Indeed, the mass of the outer shell permits the ring to exceed normal tensile strength limits on radius, as we discussed in our episode on Banks orbitals last month. By these technologies, you can take any planet, moon, or asteroid and give it Earth-like gravity, which is why I like them for options like terraforming the moon, and they are a key component of building a lot of the cooler constructs we discussed in the Megastructural Compendium, as an alternative to always using spin gravity on rotating habitat variations. Though as mentioned, we can use that to give us wide bands on the underside of each shell to also live on, and share the lighting of the next shell below it. Indeed, those bands can actually provide the active support for the shell above them. The downside of shell planets is they use way more mass per unit of living area, but a lot of it can be from low-value mass like hydrogen and helium that you are at best storing for future use in fusion or black holes. And with multiple concentric layers, or lots of vast hollow underground chambers, you can add living areas without needing more mass. Indeed, this same sort of active support technology allows you to safely shore up caverns miles wide without fear of collapse, especially without having to worry about earthquakes. And an atlas pillar losing power just begins to slowly lose strength, so it's not like you flip a switch and the thing crashes down. One made from room temperature superconductors wrapped in a good magnetic shielding needs no power after being built, in theory. I'm sure practically speaking it would lose some anyway, but might lose energy so slowly that it took millennia to get a noticeable drop in strength. And redundancy is always a good idea. Build more than you need and have plans for if someone wants to blow them up. That's a good point to close on, as I think everyone can see how awesome these things are for all the options they give us, letting us make more planets and ones closer to Earth the naturally occurring ones we'd have to terraform. Indeed, they might be better than Earth in many ways, and that includes safety. Just like a building we make can be stronger than a natural shelter, a planet we build can be tougher and safer. People hearing about shell worlds sometimes flinch from the idea of living over a black hole or a small star, or over untold tons of hydrogen gas that might vent into their atmosphere through a crack and catch on fire. These are not honestly that big of concerns, but to contrast it, remember that the planet we live on is a thin crust of rock floating on a molten sea, whose dense and radioactive core is hotter than the surface of our sun. We regularly have volcanoes go off that have more force than a nuclear bomb, and some that have more energy than every nuclear bomb we ever made, and beset by earthquakes and asteroids too. A planet we engineer and build can be tailored to minimize these things, even weather issues like hurricanes, and just represent a better option, in my opinion anyway. Let me know what you think in the comments on the episode. And don't forget to hit like and subscribe while you're at it. And to close, keep in mind that while we probably don't live on a hollow Earth, it has a lot of attractive options going for it, so we may build them in the future, and indeed we may transform Earth into one someday, and truly live on, or in, a hollow Earth. Artificial suns and sun towers. Hollow worlds and layered shell worlds raise an obvious problem. What do you use for a sky? On Earth, daylight arrives for free from a star 93 million miles away, inside a hollow planet, beneath the upper layers of Matryoshka's shell world, or on a world wandering between the stars. There may be no natural sunlight at all. Yet forests, oceans, agriculture, and human circadian rhythms still need light. That is where artificial suns come in. The name can refer to several very different technologies. At the most literal end, an advanced civilization might manufacture an actual star, assembling enough hydrogen to ignite fusion. It might use unusual fuel mixtures, such as deuterium-rich material, to make a smaller or longer-lived star, or continue to move helium and heavier elements so the star can be refueled. But for habitats, an artificial sun usually means something simpler, a machine that produces sunlight, regardless of where its energy originates. It might be powered by fusion, antimatter, beamed energy, or matter falling into a black hole. The light itself could come from lamps, lasers diffused through the atmosphere, glowing plasma, or mirrors redirecting radiation from elsewhere. This distinction matters. A black hole can be an excellent power source, but the accretion disk around it emits much of its energy as X-rays rather than pleasant yellow daylight. You would surround it with shielding and energy collectors, then convert that radiation to electricity or reprocess it into safer wavelengths. The inhabitants never need to see the black hole or its accretion disk. They see blue skies and warm sun because an immense lighting system turns lethal radiation into something useful. The simplest artificial sun might be a luminous object crossing the sky. On a modest habitat or small planet, a lamp could orbit overhead like a moon, producing an apparent geocentric world. But as a planet grows larger, ordinary orbital mechanics become troublesome. A lamp outside an enormous mega-Earth cannot necessarily complete an orbit every 24 hours, while rotating the entire planet once per day may produce enough centrifugal force to weaken or overwhelm its gravity near the equator. Past that scale, the sun does not need to orbit at all, though it needs to look as though it does. An orbital ring could carry a luminous object rapidly around the world without relying on natural orbit. Alternatively, thousands of lights mounted on the ring could switch on and off in sequence. From the ground, a bright point would appear to rise in the east, move across the heavens, and set in the west, even though no single lamp had traveled through the sky. The artificial sun would be an image produced by coordinated lights spanning a continental planet. We'd also abandon the idea of one sun and build sun towers. A sun tower is an immense pillar rising above the landscape and carrying powerful lamps, mirrors, or radiant panels near its summit. It is essentially a streetlight on a planetary scale. A world might have one towering artificial sun illuminating an enormous region, or thousands distributed across its surface. Using the Atlas pillars we just discussed, a sun tower could rise hundreds or even thousands of kilometers above the landscape, carrying lamps, mirrors, and radiant panels high enough to illuminate an enormous region. Smaller branches or suspended reflectors could spread that light more evenly, reduce harsh shadows, and simulate the diffuse brightness of a real sky. Several sun towers could coordinate to produce sunrise and sunset. One tower gradually dims as another brightens beyond the horizon, creating the illusion of a sun moving across the world. They could change appearance pass through the year, giving the habitat seasons, longer summer days, shorter winter days, or entirely new calendars. Artificial lighting also allows climates impossible on natural planets. One region might receive perpetual spring, while another cycles through dramatic seasons. Agricultural districts could use longer days and light spectra optimized for photosynthesis. Cities might receive warmer tones in the morning and evening, while wilderness reserves followed light schedules designed for the animals living there. The spectrum matters as much as brightness. Plants do not need every wavelength equally, and neither do people. An artificial sun could provide visible light tailored for human vision, ultraviolet and carefully controlled amounts for biology, and infrared for warmth. It might even alter its spectrum throughout the day, producing blue-rich morning light, a white midday sun, and the familiar reds and golds of sunset. That efficiency has limits. Nearly all the energy used for illumination eventually becomes heat. A civilization can tune the spectrum, recycle energy, and avoid wasting light where it is not needed, but still has to radiate the resulting heat into space. This becomes especially difficult in layered shell worlds, where each inhabited level adds another sun's worth of warmth beneath the layers above it. Artificial daylight may be easy to produce, getting rid of artificial summer is harder. Yet the advantage is extraordinary. Once illumination becomes infrastructure, a habitable world no longer needs to orbit a suitable star. It can exist around a black hole, inside a hollow planet, beneath 100 layers of artificial continents, or alone in interstellar darkness. Day, night, seasons, and even the color of the sky become choices rather than astronomical accidents. Artificial suns let us recreate familiar worlds where nature provides no daylight, but our next habitat abandons something even more fundamental than natural sun: the ground itself. Smoke rings. One of the most striking fictional explorations of zero-gravity living comes from Larry Niven's Smoke Rings novels, The Integral Trees, 1984, and its sequel, The Smoke Ring, 1987. Niven imagined a naturally occurring megastructure, a vast torus of breathable atmosphere orbiting a neutron star, the remnant of a gas giant planet that had been stripped and captured by the star's gravity. The result is a colossal ring of air tens of millions of kilometers across, circling in freefall with no planetary surface beneath it. Within this smoke ring, life exists entirely in microgravity. Plants evolve into kilometer-long structures, like the famous integral trees, that stretch across pressure gradients in the atmosphere. Instead of roots and trunks holding them upright, they flow in graceful arcs. Their ends drift in opposite directions, each tip forming a leafy forest canopy where life clings and flourishes. Humans, too, live here in small tribes, adapted to a world without up or down, traveling by swimming through the air, and using fire and rope as their primitive technologies. I should note that fire, much like water, acts very interestingly in Zero-G. The smoke ring setting is compelling not just for its grandeur, but because it forces us to think about what biology and culture might look like when gravity is no longer a given. Niven's tribespeople must relearn the basics of survival in 3 dimensions: how to navigate, how to tether themselves, and how to adapt socially when territory is a drifting patch of vegetation in an endless sky. For readers, it's a vivid glimpse into how alien, yet plausible, a true Zero-G ecosystem could be. Niven's not the only person to look at this idea either, so we see a variation in Peter Hampton's Commonwealth saga, and both authors explore ecology in such environs. Ecology in Zero-G. Life in microgravity does not behave as it does on Earth. Plants evolved with gravity tugging on every stem and root, and when that tug vanishes, circulation, pollination, and waste cycles no longer follow familiar patterns. Roots wander in all directions, water clings in floating blobs instead of soaking soil, and gases fail to stratify. Ecosystems in a bubble habitat would need careful engineering, fans and pumps to keep air and water circulating, genetic tweaks to help plants orient themselves, or even new kinds of crops designed to thrive in weightless space. That said, once those changes or augmentations occur, you have very nearly no size limit on many organisms. You still need mechanisms to transport nutrients and air around a large organism, which puts a size limitation on insects who have no lungs, for instance, but you could get trees that made a redwood look like a bonsai tree, and again growing out in a sphere rather than just up or down. In the bubble shell we discussed earlier, you could have trees that rose from the inner shell's ground 1,000 miles up the top shell to press the ceiling. Animals and microbes would need adaptation as well. Pollinators might take the form of swarming drones or modified insects that can navigate without up or down. Waste systems would be forced to rely more heavily on microorganisms and mechanical separators. Yet once these challenges are solved, entirely new ecological niches emerge, floating forests suspended in light, or coral-like gardens drifting in bubbles of nutrient mist. These are ecosystems that echo Earth's reefs or canopies, but freed from gravity's constraints. Anatomy of an artificial world. Whether an artificial world is a rotating cylinder, a bubble drifting through space, or a shell built around compact gravity sources, it needs the same basic organs. The geometry changes, but the anatomy remains surprisingly consistent. In a moment, we will begin to the oldest segment of the show, where my speech impediment is at its strongest, as a warning, where we will look at flat Earths or disc worlds, as not only a reminder that different shapes often still have the same design needs, but it makes me think of how often our ancestors tended to refer to the actual anatomy of the world, the bones of the Earth, or some deity it was formed from, or some mountain range as the spine of the world. And that raised our first bit of anatomy, the skeleton, the load-bearing structure that keeps the world from tearing apart, collapsing inward, or drifting out of shape. In a rotating habitat, that means containing the enormous tension created by spin. In a shell world or polyhedral planet, it may mean atlas pillars, orbital rings, or other active supports holding land above gravity sources. Most artificial worlds would probably combine passive materials with active systems, so that neither must carry the entire burden alone. Next comes gravity. That might be natural gravity from stored mass, spin gravity from rotation, some combination of the two, or classic artificial gravity that we see in sci-fi. Gravity determines far more than how much residents weigh, though. It controls where air and water collect, how tall mountains and buildings can grow, how plants orient themselves, how blood circulates through animals. It also establishes which direction counts as down. In our many artificial worlds, down may change with location. On Earth, gravity holds the atmosphere in place. An artificial world may instead use a solid roof or outer membrane, allowing it to maintain breathable air even when its gravity is weak or non-existent. That enclosure might be transparent, opaque, or layered with mirrors and screens to provide an artificial sky. It would usually be divided into many independently sealed sections, so one puncture could not empty an entire continent. Outside that comes armor and shielding. Rock, water, ice, metal, magnetic fields, and dedicated debris barriers can protect inhabitants from cosmic radiation, solar storms, and impacts. Water is particularly useful because every habitat already needs large quantities of it, and tanks placed around residential areas can serve simultaneously as reservoirs, thermal mass, and radiation shielding. Then comes the biosphere: soil, oceans, farms, forests, microbes, and atmospheric machinery. Even a habitat designed to appear natural would need immense infrastructure hidden underneath it. Pumps moving water, fans directing air, systems separating waste, and sensors tracking millions of chemical and biological variables. Nature would do much of the work, but the world still needs something resembling a planetary maintenance department. All of that machinery consumes power and produces waste heat, making the thermal system one of the least glamorous but most important organs. A planet can radiate heat from its entire surface into space. A habitat buried beneath shielding or nested inside other layers may need heat pipes carrying energy to vast external radiators. No matter how advanced the civilization, it cannot recycle heat forever. Finally, an artificial world needs a circulatory and nervous system, transportation routes, power grids, communications, repair drones, emergency shelters, and stockpiles of replacement parts. Large habitats may be divided into thousands of semi-independent regions, each able to survive while damaged sections are isolated and rebuilt. An artificial world is therefore less like a single building and more like a living organism. Its landscapes may look natural, but beneath every forest and ocean lies structure, machinery, and constant maintenance. Once those basic organs are in place, the shape becomes a choice. If you want it badly enough, they need not resemble a sphere or cylinder at all. So today we return to the Megastructures series to look at how and why you'd build a flat or flat-ish planet, as well as a few interesting variations on it. Now before we delve into the topic, I should note that we'll be assuming that gravity is being provided by classic use of mass, not centrifugal spin, as we often use for rotating habitat examples, or any high-tech type of artificial gravity like we so often see in science fiction. With that in mind, our options for construction are limited to using ultra-strong material, or what we call active support, which is basically pushing on something to keep it from falling down. We've discussed both many times, so we'll mostly bypass it today, but if you're new to the channel, you may want to jump over to the Upward Bound series or the early Megastructures episodes for a more detailed explanation. Building a flat planet, often called a disk world, is decidedly tricky even by the very high standard of building an artificial planet to begin with, and even the simplest of these would dwarf any engineering project humanity has ever taken on, and to the same degree our planet dwarfs such projects. However, it's not really a scientific challenge or super high tech, just a matter of brute force, to which more technology would doubtless help. This episode is not about the flat Earth theory. I tend to take for granted anybody watching SFIA assumes our world is a sphere, so it would be preaching to the choir, but the various problems with that theory are also some of the problems we have to overcome to make such a planet have conditions that are either Earth-like or improvements to conditions on Earth, so we will look at some of them. That's a good place to begin though. When you're getting ready to pile vast amounts of matter in place to make an artificial world, we tend to assume you go with a sphere, like Earth, as it's the version that's going to give you the maximum living area for unit of mass. That's true enough, but contains three flawed assumptions. First, it doesn't actually give you the maximum surface area for volume of mass. In fact, a sphere has the lowest surface area per volume of any object, but what's generally meant in this context by saying living area is something with Earth-like gravity, which is to say around as strong as Earth at any point on the surface, and pointed down at the ground. On a sphere, gravity always points down and perpendicular to the surface. On a cube or a disk, they do not. We also mean a place that gets enough light and warmth from the sun, and here's our second bad assumption. If I live on a rotating sphere like Earth, I have twice the land surface as a disk of the same radius, and the latter has pi r squared for area on each side, so 2 pi r squared for both sides, while a sphere has a surface area of 4 pi r squared, double a disk. Both receive the same total sunlight, assuming your disk remains stationary and perpendicular to the sun's rays. If your disk spins to receive light on both sides, it will often receive less due to being slanted. It will also have the same amount of light hitting every part of one side of that disk, whereas we get less light near our poles, which are tilted away from the sun. Now you don't have to light one of these artificial worlds with a classic star, but if you are, it has some advantages and disadvantages, because while a flat planet gets the same light everywhere, a spherical one loses a lot of real estate to being too hot or too cold. When you build a flat planet orbiting a star, the whole thing has mostly the same climate, meaning you have less real estate, but you can use every little bit of it. The third flawed assumption is that you actually care about how much mass you are using. It takes far more mass to make a classic mass gravity planet than a spin gravity one of the same living area, by many orders of magnitude, which we covered the specifics of in the episode Mega Earths. So if you're making a spherical planet, it already implies you aren't trying to optimize that. If you're already using 1,000,000 times more mass to build a spherical planet instead of swarms of rotating habitats of an equal living area, going up to 2,000,000 times isn't that big a deal. Now you might say that highlights a problem right there. You wouldn't build these natural gravity worlds because they are mass wasteful. Except they are not. They are not expending mass, they are storing it, and it doesn't matter what kind of mass it is. Earth mass is about 6 zetatons, mostly iron, oxygen, silicon, and magnesium, but to produce gravity, 6 zetatons of hydrogen and helium work just as well, and they are each far more abundant than every other element combined. The only source of gravity more abundant is dark matter, and if we ever figure out a way to capture and store that, it would work too. Hydrogen is very valuable to civilizations that run on fusion, be it artificial fusion or from a star. You need to store it somewhere, and a big spherical or disc-shaped tank that you've slapped a layer of dirt, water, and air around works just fine. You'd have to haul it out of a gravity well, but the energy released by fusing a kilogram of hydrogen is so much more than the energy needed to lift it out of an Earth-like gravity well that it can be disregarded, and you could have derived a similar amount of power from it while dropping it down that well in the first place. When you're storing hydrogen gas for billions of years, it's very likely to leak out if the gravity pull isn't much higher than the kinetic energy of those hydrogen atoms in your containment vessel. So while you'd expect most folks to live inside cylinder-shaped rotating habitats, you'd also expect a proportionally small but still large number of these kinds of artificial planets that use natural mass-based gravity as it serves as both storage and living area. What the filler is would vary. It might be their fuel reserves or their temporary trash cans too. By default, we assume advanced civilizations use hydrogen turned into helium for energy. And helium is actually a pain to use for gravity because you have to build very large to overcome its low density. But they might be able to fuse helium into carbon, or nitrogen or oxygen, or even go all the way up to iron, which is great for building smaller, natural gravity planets, as it's very dense. Of course, they might feed matter right into black holes for power production, in which case it doesn't matter what type of matter you use. We'll discuss many other advantages of flat planets as we go, but think of it this way. If you're storing huge amounts of raw material someplace, you might as well get some extra use out of it by living there. And if you're engaging in the kind of stellar engineering we discussed for things like star lifting or extending a sun's lifespan, especially the latter, you are going to end up with tens of thousands of planets worth of excess mass whose value is huge, but only in the context of being able to use it billions of years from now, which makes it perfect for a planetary storage system. Now, if you go fill a giant hollow planet with gas, you can actually rely on pressure to hold the surface up, like a balloon, for certain sizes and pressures anyway, or some super strong firmament material if you had it, but you'd usually end up using a big, spherical shell made out of overlapping orbital rings. See that episode for details, or again, mega-Earths. For non-spherical planets, you pretty much have to do this anyway, because on a flat, thick disk of a planet, gravity only points down at the middle. As you move out from the center, it will start tilting toward the center instead of straight down, and left to its own, you'd end up seeing the disk deform to have a bulge in the middle, what we call a pancake planet, and eventually turn into a sphere. A pancake planet has some advantages too. You have a horizon on one from the curvature. On a strictly flat planet, you do still have an effective horizon, as the light traveling through all that air will get blurry and bent, but it's a long way off. Interestingly, on a big enough disk world like an Alderson Disc, a version billions of times bigger in area than Earth, you would have to consider the effect of gravity on the light too. If someone far off points a laser your way, the beam will curve down and hit the ground before reaching you. But if they angle it up a bit, it would curve down and reach you, like throwing a ball which follows a parabolic trajectory. That would seem to give a horizon, but that whole disk will have light heading up at angles too, which will curve down and reach you, so that even though you are standing on a flat surface, it will seem to curve up. We'll discuss Alderson discs another day. For our more modest flat planets, if we want gravity to point straight down, we have to distribute our mass differently and not uniformly. To avoid that slanting effect as you move out from the center, you need to increase the amount of mass under you as you go. Though you can also spin the planet like a carousel to get centrifugal force, which would push out, helping to counter the central mass, and it will rise as you move out from the center too. Imagine for the moment our flat planet was made of many concentric rings, each a bit more massive than the next, growing as you move to the edge. We will also spin it, and we will balance the whole process out for whatever combination best achieves a mostly uniform gravity pointing more or less downward. It need not be perfectly uniform either. Earth's gravity isn't after all. It's lower or higher depending on your altitude and latitude, and it does angle near mountains and cliffs, which pull you a bit sideways. Now, since I raised those rings, let's take a moment to remind everyone what an orbital ring is. An orbital ring is a hollow ring around a planet that is basically stationary relative to the planet's surface. Inside it is a vast amount of matter spinning around faster than normal orbital speed, and the net momentum of the hollow stationary part and the inner spinning part to add up to whatever the appropriate momentum would be for an object of that total mass to orbit. Visually, think a big long hose wrapped in a circle with water spinning around that loop. And again, see the Orbital Rings episode for the specifics on that. We call that active support, and we have a few types besides that discussed in space towers and launch loops and some other episodes, but we'll focus on the orbital ring. We will make a ton of them, each a bit wider in diameter, laid out as a disk. We will pump a huge amount of matter through them, probably hydrogen or helium, which we've compressed to a high density. So it's a good chance it's metallic hydrogen, which is handy if those rings are using magnets or superconductors to keep the mass spinning. You would increase the density in each subsequent ring so it had more mass, or put more rings below them. 2 quick notes. If for some reason you can't compress your hydrogen or helium enough to keep things decently flat for a coin-shaped disk to live on, rather than a thick cylinder you'd live on the caps of, you do have a couple of options. First, you can use artificial black holes instead. Those do have magnetic fields you can push on them with, and they could orbit inside a hollow tube just fine. Second, if you got to make it deeper as you go out, you can opt to make it taller instead, sloping your world up near the edges, rather than the middle like the pancake planet. Those sloping sides, like a bowl, let you add more mass and also tilts the gravity more outward, counteracting the slant toward the center. Some folks might object to living over the top of a bunch of black holes or ultra-compressed hydrogen, but just as a reminder, we all live on top of a vast, molten, radioactive ball of metal. The solid part we live on, the crust, is about as thick and sturdy as that nasty skin that forms on top of hot soup or pudding. Assuming you can get those materials in the ring dense enough, you can go ahead with your entirely flat planet at this point. Otherwise, you might need some curved geometry, and we'll discuss a few other fun options later. Your next step, though, is to lay down a normal layer of artificial land and sea. And this is obviously no easy process, but in terms of effort per living area, this phase is no harder than terraforming planets or building rotating habitats. Your flat Earth has no real horizon, but it's still better than a rotating habitat in that regard, where the ground curves up and your neighbor's backyard hangs over your head. Here it just goes on forever until interrupted by air interference and blur, or landscape. That's another trick for handling gravity slanting issues too. You can build mini layers of circular mountain ranges whose extra mass yanks material toward them, keeping air and water from drifting off too much, breaking up horizons, and letting you tilt land to match slants with less of an issue. An extreme form of this is the ripple world, where it just moves outward like a wave of peaks and valleys from the center, differing from a ripple caused by dropping a stone in a pond, in that the further out from the center you get, the higher those waves would be, rather than attenuating off in amplitude or height. The planet would still look rather flat from a distance, but to those living on it, there would be more natural landscape curvature. Playing with the landscape this way also helps break up the weather and climate. Again, a flat planet has the same lighting and temperature everywhere on a given side, and while you might prefer that over land wasted on equatorial hotspots and frozen poles, a little variety would be nice. Speaking of lighting, that's the next big issue. Now, unlike the flat Earth theory, our flat planet can just be orbiting the sun and spinning like a coin for day and night. And we can tilt it too so it has seasonal variation. The sun would otherwise rise and set just like normal. Twilight and dusk are a bit different, but there is still a horizon in this regard for it to rise and set across, and you'd still get that noon blue and twilight red. However, such constructs require huge amounts of effort and energy that you likely can only afford in scenarios where you can mimic the sun anyway, via artificial fusion or huge mirrors or Kugelblitz black holes, so we might prefer to go the flat Earth approach on this one. In the flat Earth theory, the sun is not a giant, far from Earth and nearly 1,000,000 times more massive. It and the moon are fairly tiny objects that just circle over the Earth, about where the equator is, a circle about halfway out from the center of the disk, with the North Pole at the center, and the South Pole as a circle on the rim, both far from the sun and moon. Now this begs the question as to why the sun does not fall down. As I recall, under flat Earth theory, this is because gravity is much weaker and diminishes faster than in Newtonian physics, somewhat akin to an extreme form of MOND, modified Newtonian dynamics, that sought to explain dark matter as a false positive caused by gravity getting weaker faster than the inverse square at very large distances. We are assuming throughout this episode that gravity works more or less like Newton and Einstein said it does, and that we have no artificial way of messing with it beyond piling up mass somewhere or spinning things very fast. In this case though, we are obviously not dealing with a typical star, so we need not assume it's that massive. Such an object needs to be putting down around 200,000 terawatts on our flat Earth, assuming it's got the same land area as Earth, and presumably be about 30 kilometers in diameter to be about the same size as the sun or moon in the sky, if about 3,000 kilometers above the equator, implying that each square meter of that sun disk object was giving off about 7 gigawatts of power. Imagine for the moment that our sun here was a big flat mirror or solar sail, and that we were beaming lasers or light beams at it that it bounced back down to the flat planet below. If you've seen the Interstellar Laser Highways episode, or any of the ones we discussed laser propulsion spaceships in, you might remember it takes either 3 gigawatts of laser per ton absorbed, or 1.5 gigawatts when bounced instead, to accelerate an object at 1 g, or hold it stationary against Earth's gravity. We'd have enough power per unit area here, 7 gigawatts per meter squared, for a very thick mirror, indeed one thicker than battleship armor rather than the thin foil we normally think of for solar sails and mirrors. So that part at least is easy. Such a fake sun can be held up either by its own internal power generation or by light it is reflecting from the true source. That's also more than enough energy to let you steer the thing around in a circle. Similarly, a big internal fusion plant could be grabbing up trace atmosphere to superheat and use as exhaust. One problem is that for that size and power, your black body spectrum corresponds to more than twice the sun's surface temperature, which is obviously a problem for building an object to generate this, since it would melt it to slag, and also be generating a lot more ultraviolet light than we'd like. Not as big a deal for mirrors though, since they'd be reflecting most of the light away, not absorbing it, and are of course mechanically simple, so can better handle heat anyway. Now conveniently, a black hole producing this amount of energy via Hawking radiation only masses 40 kilotons, and even using just a small portion of that as thrust would be enough to keep it aloft. However, it would only live a couple months, so you'd have to be constantly feeding it. You'd probably use many of them clumped together with more mass, longer lives, and less power output. You'd also need to surround it with something that could absorb all that gamma radiation and spit it out as normal light, same as our sun actually does. We'll discuss this more in Making Suns early next year, where we'll look at both building the natural kind and all sorts of pseudo-suns we can make via artificial power sources or black holes. But for the moment, we'll just say the mirror approach is probably the best one for doing this variety of lighting, where the sun spins around over a flat planet, and you'd probably fake the moon the same way, or moons if you wanted to. You also need another sun on the other side, unless you want to waste half your flat Earth's potential living area. The other option, which we'll also discuss more in Making Suns, is a sun-moon, the classic geocentric one where the sun is a moon-sized object orbiting the planet. Couple caveats first. For any given object, there's only one distance in terms of orbits that is going to produce a 24-hour orbit, which can be a pain for getting your sun in the right place,
We can counter that by spinning the planet too, with the sun, moon, or backwards. For instance, if the sun did orbit the Earth every 24 hours, it would hang in the same place because the Earth spins that fast. That's a geostationary orbit. Alternatively, if the planet spun backwards, in such a case the sun would take less time to re-illuminate the same place. So we can do the same thing with a flat Earth to widen our options, but you can't spin such an object very fast. Indeed, that's one of the problems with using the real sun for lighting if you try to make these places much bigger than Earth-sized, too much centrifugal force on the sides. If you want to scale a disk world up, you need to make it an ellipse instead of a circle so you can spin it relative to the sun without getting extreme forces near what I suppose we will call the equator. You might do that for one with a sun-moon too, since an orbit around a big disk is not quite the nice circle or ellipse that it is for a sphere, especially a disk with a non-homogeneous distribution of mass. Now, your fake sun gives a lot more of its light to your planet proportionally than ours does, but it still wastes a lot of it by radiating omnidirectionally, so you'd probably have a big spotlight or parabolic dish arrangement for your sun rather than a uniform light bulb, and that helps a lot for trying to get the fake sun to be the right size and orbital rate and brightness and spectrum. You could also use the same tricks as with the hovering sun from earlier though, since all that power can be used as thrust to let you get around the normal orbital mechanics for time and distance. Of course, you can circumvent all of this by just having giant lights overhead that switch on in sequence to fake a moving sun, or using a big spaceship that flies around lighting you with its engines, sort of like Helios and his sun chariot from Greek mythology. Heck, it might even land in some sea on the rim to refuel with water for thrust and hydrogen fusion fuel every night. Seems kinda crazy as a very extreme effort, these sorts of things, but keep it in context. You just built a whole planet shaped like a pizza, which dwarfs this type of fake sun building. Okay, that's the basics. Let's add some options for variation or adding these things together. One of these is a roulette world, where like a roulette wheel, it bulges up on the rim and the middle. Actually, this is one of the variations used for the flat Earth theory, and it gives you better horizons and better light distribution if you're using that hovering but circling sun approach. It's also much easier to build, since you can have a central mass and a lot of other mass orbiting normally in a hoop around it. Then just build a layer over top, curved to keep gravity perpendicular to the ground. You can later expand this with more rings to create the ripple world we mentioned earlier. With any of these, you also have to decide what to do with the sides or rim of the planet. You can let it flatten off as a straight disk you'd sail over the edge of, but you wouldn't fall forever, and depending on how you did your lighting and mass distribution, this might be a forbidding dark frozen wasteland, or just a curved rim, maybe habitable. Unless you're building much smaller than Earth, there's no need to have rim walls for retaining air or keeping things from falling off, as gravity still pulls on everything, not just straight down relative to the ground. And of course, so long as it's lit, this area, the edge of the coin, is entirely habitable with gravity pointing the right way. Curve it, and it has horizons too, and you can just walk, sail, or fly around it to the other side. Assuming we're using one lit by our own sun, again, you can just spin it on a side, and so long as it's not too big, you don't have to worry about it flicking people off the nominal equator, so don't build one bigger than a gas giant unless you also want to start distributing your mass non-homogeneously in that way too. Which you can do. Orbital rings aren't the only trick for that, and need not be circles anyway. You can use what we call an Atlas pillar, for instance, too, which is essentially a space tower, a straight structural member in which accelerated matter shoves at the ends to give it an arbitrarily high compressive strength. One can think of these as orbital rings of very high eccentricity. See the Space Towers episode for details. As to arrangements, if you're providing your own lighting or using beamed-in light off a big hovering mirror, you can put these anywhere you please, but if you want them using the sun, then you'd put them in a big ring around the sun out as far as Earth. You could pack in tens of thousands of them in one orbital plane, which is also about all you'd have the mass for, if you were stealing that mass mostly from the sun via star lifting. And of course you'd need to go in closer, as the sun would have gotten a bit dimmer as you stole its mass and extended its life. Since they are flipping around, a lot of that sunlight would be wasted, so you'd probably put a big thin ring world covered in solar panels behind them, or maybe a variation on the rung world we discussed in Dyson spheres. There's some weird tricks you can do to allow you to travel easily, maybe even walk between such collections of planets, but we'll discuss those another time too. As to why you'd ever build such things, it's worth remembering that any civilization that can build such things is one powerful enough to justify the efforts simply by saying, because we can. However, as mentioned earlier, they do serve an actual purpose. You can store mass in many ways, but if your civilization is going in for the long haul, you do need huge reserves of mass, and ones that can reliably be kept securely for astronomically long times, quite possibly more than an entire solar mass, as your home system might be grabbing additional material from nearby systems. Most storage spots would probably be spherical shell worlds, and they'd only be a small fraction of the places people lived, but there's no real major downside to using other geometries that would prevent you from doing some for novelty value. A flat Earth is going to be a major tourist attraction, and one which conveniently has good weather everywhere on it, no polar or equatorial variation, so you could cover it with tons of archipelagos of snaky islands and beach resorts, for instance. For that matter, you could also recreate Earth-like deep oceans, something that is very hard to do with rotating habitats. So this is an example of a type of megastructure and artificial planet that you wouldn't build a lot of, but which you probably would build some of. So while in the past folks often incorrectly believed the Earth was flat, in the future there will probably be folks who would say that and be correct. It does make me wonder though, if any of those folks living on a flat Earth might create conspiracy theories that they actually lived on a sphere.
Sombrero Planet. We have just discussed flat Earths, but I want to linger on one variation I came up with while writing that episode back in 2018, the Sombrero Planet. It was only a side idea at the time, yet stayed with me for the 8 years since, partly because it may have been considerably more practical than a perfectly flat world. Before returning to it, a quick production note though. It is probably impossible not to compare my present voice with the recording from 2018, which was already made more than a year into speech therapy. We also have 2 still order episodes from 2016, Shell Worlds and Disc Worlds and Alderson Disc. Those were our first 2 weekly episodes, back when they still appeared on Fridays or Saturdays. The regular Thursday schedule began about a month later. Neither is included here. My speech impediment was simply too pronounced in those recordings. So rather than trying to splice them into this compendium, we've replaced the Alderson Disc material with a new segment. We will probably revisit and expand both order subjects properly at some point. Returning to flat Earths, their appeal lies partly in their simplicity. Provided the world is not too large, you could tumble it through space like a coin, alternately returning each face toward the sun and producing something resembling a 24-hour day. Larger versions would probably use artificial suns instead, because rotating an enormous disk that quickly would eventually produce more centrifugal force than we want. The harder problem is gravity. On a uniformly flat disk, gravity does not point perpendicular to the ground everywhere. As you move outward, it increasingly pulls inward toward the disk's center. Water, atmosphere, soil, and anything not firmly anchored will tend to migrate that way. You can compensate by redistributing the planet's mass, placing more beneath the outer regions. That creates another problem. What are we making this world from? One likely answer is hydrogen and helium. They are overwhelmingly abundant, useful as a fuel, and something an advanced civilization may need to store in colossal quantities anyway. Rather than leaving those reserves in featureless tanks, we could use their mass to provide gravity and landscape the exterior into an inhabited world. Unfortunately, hydrogen and helium are not very dense. We could compress them into denser shapes, perhaps including metallic hydrogen, or imagine more advanced methods for stabilizing extremely dense or even degenerate matter. But compression requires pressure and energy, and push hydrogen hard enough and it becomes inclined to fuse. A small flat planet made mainly from those elements may therefore need to be surprisingly thick, and making its outer regions denser still becomes increasingly awkward. The Sombrero Planet approaches the problem geometrically instead. Rather than insisting that the inhabited surface remain perfectly flat, we shape it to follow the local gravitational field. The center rises into a broad crown, surrounded by an immense annular basin or trough, while the outer brim curves upward. Seen from the side, it resembles a sombrero, or perhaps a very strange inverted pancake. The important point is not the name, but that the ground is arranged to remain approximately perpendicular to local gravity. Down may still change direction as you travel, but it remains mostly in the landscape rather than sideways across it. Oceans in the atmosphere can spread through the broad basins instead of draining to one central pit. This also reduces how much the solution must come from extreme density. A world can be made larger and more gently curved, with stronger partitions separating reservoirs of hydrogen, helium, water, metals, and other stored materials. Some rotation could keep the mass distributed toward the outer brim, while pumps and active support handle the remaining imbalance. The central crown and surrounding trough also offer interesting lighting options. The entire planet may tumble slowly in natural sunlight, or artificial suns could circle the crown, shine from towers along the inner slopes, or appear to travel overhead through sequential lighting. Different rings of the world could have different days, climates, and seasons. You may even have what we may call a ripple world, where you have multiple concentric rises in the land, getting taller as they go further out. The opposite of what ripples normally do when emerging from a point, like a drop of water hitting a pond. There are other options too, and perhaps it will get its own episode one day, but the Sombrero Planet is not merely a flat Earth with a hill in the middle. It is what happens when you let the shape of the landscape cooperate with gravity instead of fighting it. And that landscape need not be dominated by land. We often discuss habitats in terms of how much surface humans can walk upon, yet about 71% of Earth is ocean, and much of human civilization is always clustered near water. Artificial worlds might favor long, winding continents and countless islands to maximize coastline, but it can also be built around truly deep seas. That is something most routine habitats struggle to provide, and leads us to our next chapter, Oceans in Space. As we move into the future and expand off planets, we tend to design our megastructures and habitats to our own bipedal, land-based desires. But what about our oceanic friends, like super smart dolphins, or if we find marine life in the ocean moons of Jupiter, or if we decide to re-engineer ourselves into more men and more maids? So one of our most talked about topics on this channel is the general concept that humanity is likely to build giant space habitats as opposed to simply terraforming and colonizing other planets. And today we will be discussing that notion in the context of building oceanic and aquatic habitats in space. We will introduce some new megastructures like a hydroshell, which allows truly huge aquatic environments, dwarfing planets but avoiding crushing water pressures. We will be looking at this in terms of a few options for gravity: microgravity, gravity simulated by rotation, natural gravity, and artificial gravity. We will be looking at scales from small habitats up to planet-sized ones, and even ones dwarfing planets in scope. We will also be looking at purposes, whether it's a civilization that's aquatic in nature or it's more of a preserve, such as if we built large marine habitats as nature preserves rather than for us to live in, or for highly uplifted dolphins or whales to live in. We will also play with some interesting features you might have in these, like vertical reefs or submarine islands inside and under the water. Now, to begin our discussion, there's two critical concepts we need to understand. First, that water under gravity will grow in pressure as you go down, each layer above pressing down on you more. And second, that gravity can be mimicked by rotation and centrifugal force, and water will still grow in pressure under that pseudo-gravity. This is going to cause us some problems that, as we will see today, make it tempting to either minimize gravity if you can, or opt for small rotating habitats, or rather, skinny ones. Also, we need to understand that whirling an object around to create this pseudogravity puts it under tension. Whirling a stone around on a rope makes that rope taut, and if you spin it fast enough, or use too big a rock, the tension will rise too high and will break that rope. How strong a material is in this way is called its tensile strength. Normal gravity can break stuff too, under sheer weight of stuff piling on it, compressing it, and this is called compressive strength. Materials have tensile strengths and compressive strengths, and the two have little relation. A given material can be very strong in one of those strengths but weak in the other. How fast you spin a cylinder, combined with its radius or diameter, will control how strong gravity is at the surface. It is linear too, so halfway between the center and the edge, it's half strength, and 0 at the center. This tension on the material the cylinder is made out of is essentially identical to what a suspension bridge here on Earth experiences, and a bridge a kilometer long would need the same strength as a cylinder habitat a kilometer in circumference, or 0.16 kilometers in radius, or 520 feet in radius. Steel can handle such a length or circumference or radius, but it is quite a burden on it, and only made worse by adding materials, such as lots of cars and trucks driving on that bridge, or all the concrete or asphalt making the road on it. Same for cylinder habitats, all that dirt and water inside them add up, and a few meters of dirt is pretty heavy, several tons per square meter, so we tend to think that any hills inside such habitats would be hollow, filled with tough but ultralight fillers like aerogel that could be covered with a thin layer of dirt, or by putting dimples and rises in the hull itself. This mostly works because land-based life is really pretty two-dimensional. We have plenty of hills and valleys, but it's the surface we live on, and a house at the top of a hill and one down a valley still have a basement and second floor just a few meters above or below that surface. Marine life is a bit trickier. Our oceans here on Earth average about 3,000 meters in depth, and each meter of depth represents another ton per square meter of stress. So whereas a thin coat of dirt a few meters or 10 feet deep might put 10 tons of pressure per square meter down on your drumhole, a few kilometers of water would put down 3,000 tons per square meter. That means your hull needs to be 300 times stronger to handle such depths of water inside. Now there's a couple caveats here, and the first is that, as I mentioned, gravity experienced inside a rotating habitat is linear to how far from the center you are. So the upper layers of water inside such a habitat push down less because gravity is weaker up there, though only if that habitat's radius is fairly similar to the water depth. If the habitat is 1,000 kilometers in radius, then even if your ocean is 10 kilometers deep, the top is only experiencing 1% less gravity than the bottom, and it's fairly trivial, much as the change in gravity on Earth from altitude or depth is when we're only talking about mountain peaks or ocean trenches. But what it means is that a cylinder full of water a kilometer in radius is only getting about half the stress on that bottom as that depth implies from the weaker gravity, 500 tons per square meter rather than 1,000. Also, it means that you have a 2 kilometer wide stretch of ocean there, since it's water all the way through and its diameter is 2 kilometers. Though you might want a layer of air in there. And we probably want to ask why we need that much depth. There are creatures living in the deepest part of our oceans, fully 11 kilometers deep in the Mariana Trench, and we may want to simulate that environment or even higher pressure ones. However, the overwhelming majority of ocean life lives in the epipelagic zone, the thin-skinned 200 meters deep where sunlight can still meaningfully penetrate water and fuel photosynthesis. On our planet, that epipelagic zone also fuels what life is below it, as things either swim up there for food, hunt things swimming down from there for food, or wait for dead matter and detritus to come falling down, what we call marine snow. Now, there are geothermal vents and such fueling some life too. Indeed, the principal current theory on the origin of life puts those vents as the best candidates for life to have emerged at, and been sustained by until photosynthesis evolved a billion years later. We can replicate such thermal vents on a space habitat, of course, and one of the cool things about artificial worlds is all the flexibility you get. They are the difference between living in a natural cave and a well-built mansion. If you want a habitat dense in life but only running on geothermal vents, you can do that, and create worlds worth of ecosystems for all those life forms confined to those tiny undersea oases of heat and life. That might be some interesting engineering too. You might have a nuclear reactor's secondary cooling circuit venting directly into the hab. Water coming from vents needs to be highly mineralized, so you would either need a tank of dissolved minerals to inject into the stream of hot water, or solid mineral blocks that are dissolved by the hot water. Either way, your engineering would need to avoid minerals precipitating onto critical components like turbines or nozzles. Key thing about megastructures, they do need maintenance. You might instead opt for something like a passive decay radioisotope supply, or even the natural fission reactors that sometimes formed in Earth's deep past around uranium-rich pockets. With artificial habitats, we so often focus on using the sun or mimicking it that it is easy to forget that we have some other options for life. Nonetheless, virtually all the life in all seas lives in that sunlit epipelagic region or close to it, so we could build a skinny habitat just 100 meters in radius, reflect and pump sunlight into it, and actually get some fairly interesting currents and motion going from all that spin and varying gravity by depth. The smaller a habitat is and the faster it rotates, the more pronounced the effect of gravity varying by height, and also the Coriolis force, which is another fictitious or inertial force like centrifugal force related to spin, and one strong enough that it's a big player in all weather, in spite of Earth being wide and slow spinning. We will be talking about suspending islands or reefs in bigger water habitats later today, and these weird currents are one option for doing that, as rocks should fall down, but much as gliders can remain hanging in the air by using rising currents of moving air, you could get some metastable pockets of ocean on your habitat where coral reefs glide or hover on currents of moving water. You also have the ability to hang your islands by a tether from the center, which is exactly as sturdy as the hull since it uses the same principle of tensile strength, much as islands and continents use compressive strength here on Earth. The cool difference is that tensile strength is generally flexible, so a big rock floating in the middle of a marine hab held by a tether to the center could also move around and twist like a pendulum. So imagine a big three-dimensional ocean with submarine islands moving around, underwater, on their own orbits and paths, circularly, elliptically, and potentially all sorts of zigzags, especially since one cool thing about a tether is that you can winch it up or down too, and run power down it, for engines or turbines or air compressors. Part of the reason our oceans are so dead on a volume-by-volume basis with land is that in spite of being huge in resources and sunlight, those two are not in the same place much. With the exception of a narrow band along the coast, most of the nutrients in the ocean sit on the seafloor in darkness, whereas most of the sunlit part of the ocean is starved for nutrients. An engineered ocean habitat is capable of using water currents and lighting to bring nutrients and light wherever they are desired, extending epipelagic zones indefinitely. We often discuss doing this for Earth's oceans or subsurface oceans like we expect to find on icy moons, like Europa or Callisto, and I call them vertical reefs, as one would expect these chains of light to result in fairly parallel roars to what normal reefs do, creating dense local pockets or ribbons of ecology and biomass. Indeed, we tend to assume lighting on rotating habitats will be artificially generated to begin with for many hab designs, generated by electricity or moved in by mirrors or fiber optic cables, and I would say this would be a common approach except for one big factor: hull stress. We don't really want to involve deeper layers of the sea except where it's either needed for the ecosystem to function, or because that is the ecosystem we are making because it's supposed to be simulating the Mariana Trench, not Caribbean archipelagos. If we want to make strictly epipelagic lit regions, only more of it, we opt to make our habitat longer, not wider or deeper. Once you get to that peak radius and depth for your sea based on your needs and material constraints, you don't build any wider, you just build longer. Your cylinder becomes more of a skinny pencil or needle shape, or even a very long sausage-like linked arrangement of many chained together, or a rope like a mega-long hab, what we call a topopolis, which might be millions or even billions of kilometers long, but only a few kilometers wide. Such long habs or sausage-link affairs are good ways to place similar but distinct ecosystems nearby in a way that allows only the amount of interchange that you want between them, as a means of controlling invasive species or encouraging migration. So what if we want really deep oceans but don't have the materials for it? Nothing strong enough or cheap enough? One thing to remember is that a lot of the ocean's dependence on gravity is just to keep things moving from above to below, and we are quite capable of pumping nutrients and air bubbles around inside a microgravity environment too. But as I mentioned, we think a lot of icy moons might have subsurface oceans, and they are considered strong candidates for extraterrestrial life, albeit probably low in biomass and biodiversity from the lack of sunlight. We tend to assume the lower gravity is not an issue there, where it's often weaker than our own moon, and there are good odds Earth-based marine life would require little adaptation to lower gravity, say a tenth of Earth normal, and that right there lets you seriously increase your depth of sea and radius of habitat, because it's still enough for there to be a real and meaningful concept of up and down, but each layer of water presses down less. This potentially allows much deeper layers of ecology in your habitat, as pressure will shift more slowly with height. It is too soon to tell if low gravity is viable for terrestrial marine life. Zero gravity seems to have been rough on fish we tested thus far, and even if low gravity is, it might be viable but require lots of adaptation, natural or genetically engineered, which somewhat defeats the point of building a nature preserve. We will have to see on those, and it might turn out we need full gravity, in which case we might need to be considering using rare oceanic planets of the right gravity as those preserves, or very long thin water habitats. One other option though might be a shell world. Now normally we contemplate this as a hollow metal shell with dirt and water on top of it, with either a black hole or compressed hydrogen or helium inside, serving as an abundant and cheap source of natural gravity. However, a hollow sphere itself generates gravity with the normal properties by and large. The difference is that all your gravity is generated by that shell, and its higher layers exert no gravity on its lower layers, so that counterintuitively, the gravity decreases as you go down the layers. It still pulls inward though, it's not reverse gravity. This has some interesting options for habitats because a sturdy hollow metal shell with some rock over it, nothing under it, and many kilometers of water above might make for a huge and viable ecosystem dwarfing anything Earth could have. In our discussion of super-Earths last week, I mentioned that since Earth is 5.5 times denser than water, a planet with the same surface gravity as Earth, but composed entirely of water, would be 5.5 times wider than Earth, with over 30 times the surface area and obviously much deeper seas. But if those seas weren't very deep at all and just ended with a rocky shore and hull 10 kilometers below, things shift quite a lot. Incidentally, if this shell world and how it's not collapsing downward is a new concept to you, see our Mega Earths episode for a discussion of the mechanics and technologies required. Otherwise, just assume it's magically strong material for now. Water is ridiculously common in this universe, albeit mostly as ice, and coming up with entire planetary masses of it is much easier than coming up with rock or steel or even air. A spherical shell 10 kilometers thick of Earth's mass in water and some rock and hull would have a volume of 6 trillion cubic kilometers and a surface area of 600 billion square kilometers, about 1,200 times that of Earth's surface, and a radius of 2,220 kilometers, 34 times that of Earth, and over half the distance out to the moon, closer to the size of a star than a planet. However, because it only has Earth's mass, the surface gravity would be 34 squared or 1,200 times weaker, amusingly meaning the pressure even 10 kilometers deep would still be less than 1 atmosphere, Earth normal pressure, before even accounting for the drop in gravity as you went down, which for these shells much thinner in thickness than in radius would be linear to how deep you were. Now, critically, if you double the structure's radius but keep the same thickness of sea, 10 kilometers, that surface gravity will stay the same because you quadruple the surface area and thus quadruple the mass, resulting in same strength of gravity no matter how big you go, and you can push this up to Birch Planet scales. Galaxy mass artificial planets, again see the Mega Earths episode. However, if we increase thickness a bit, say to 1,200 kilometers deep, then we've got 120 times the mass or density on these objects, for a surface gravity a tenth of what Earth has, meaning pressure is only rising at a tenth the rate, and will actually rise slower as you get deeper, and those higher levels of water cease contributing to the gravity pulling down. Any spherical shell of mass generates no gravity inside it, be it one step inside or at its center, so way down at the bottom, 1,200 kilometers deep, over 100 times the depth of the Mariana Trench, our pressure is only a 20th of what we would expect, albeit 5 times higher than at the bottom of that trench. One where the water was only 120 kilometers deep, giving only 1% of Earth normal gravity at the top, would be one where you could swim around with normal scuba gear all the way to the bottom. This also means biological life can run that whole range, especially with supplemental lighting such as vertical reefs, and with heaters and pumps and mixers down on that shell, you could simulate thermal vents too and massively more densely. So you could get some huge depths of ocean habitable to life and densely so. Oxygen is incredibly common and hydrogen vastly more common than that, but even without putting much effort into cramming them together, we get estimates as high as a dozen times Earth's mass in water in our Oort cloud alone, which for the 120 km deep shell example would result in a shell as big as our force-thin version, 1200 times Earth's surface area, all of it composed of a massive sea of low pressure. I am going to define worlds or megastructures of this type as a hydroshell world or just hydroshell, one where the water pressure doesn't rise beyond anything we find on Earth, indeed may stay well short of it, but which is huge compared to Earth, and we will just prefix kilo, mega, giga, etc. under hydroshell for its total mass relative to Earth. This is, to the best of my knowledge, a totally new type of megastructure that came to my mind while writing the script with the power flickering here at home from 40-mile-an-hour winds and plenty of rain, so I doubt I've done more than scratch the surface of what these surface shells of sea might offer for combinations, and I'd encourage all mini math and world-building savvy folks to play with the options on the idea and let me know what you come up with for options and limits. Same for our Topopolis sea worlds. One that comes to mind is neutrally buoyant submarine habitats with air-filled domes that are pressurized to right around the 1 atmosphere mark, since the dome would have no real stress on either side of it, making air bubble submarine island habs a real and decently safe option. And you could play with partial pressure and air mix to let your islands be at various depths. These could get big too, continent-sized, complete with kilometers of vertical change in terms of mountains and valleys on them. They could also be very three-dimensional rather than just that classical image of a thin island with a big dome over it. You probably do lots of bubble domes instead of one big one, and you probably have lots of gas packed in your rock layer like aerogel below the ground to help with buoyancy, but this offers some huge options for habitable land on such worlds, which again can be hundreds or even millions of times Earth's surface area. Any rock in your hab that is exposed to water would become coral reefs, which would be just delightful. Of course, you have the option to genetically engineer gills into folks for your mermen and mermaids, but I suspect a nice safe dome operating well under known cracking pressure would be preferable for most potential colonists. This would work on subsurface oceans of icy moons too, as they have low gravity and a similar slow rising pressure scale. We also have the option of an oceanic hoop world, though we'll save discussions of that for another time if we ever remake our old Hoop Worlds episode. Needless to say, if you can create gravity artificially like we see so often in science fiction, or have anti-gravity, you have some additional options for big water worlds. Now it also might turn out that gravity is not needed for marine life, or you might choose to genetically engineer all your marine life to no longer need gravity, which sure makes building such habs easier, though so long as little gravity is needed it shouldn't pose too rough an engineering hurdle, as we've seen. And if we are actively pumping air bubbles and nutrients around our habitat anyway, then we need not rely on gravity alone for that sort of effect. The problem is at a certain point, you do get gravity if the habitat is big enough, but we are talking hundreds of kilometers wide before it even got to 1% of Earth gravity, so you can make some very big marine habitats in microgravity, but as they get bigger, they get more gravity. One option though would be something that is mostly water in the large moon range of mass, and which had an artificial sun at its center. Such a water globe might have an atmosphere outside, or a layer of ice as its skin, or a metal hull, depending on size and engineering concerns and preferences. This central sun need not be sun hot, it could simply be light generated by LED, but it is worth noting that at a certain sweet spot of temperature and gravity, water falling down on a white-hot pseudosun is going to evaporate faster than it can fall and shove water back up too. This should seem to create some sort of brilliantly bright, bubbling eternal storm at the center, which would be quite a cool effect, I'd think. However, I could definitely see a lot of those sorts of artificial stars, scaled down to something more like a big power plant, floating around these sorts of world seas. You might intentionally power them up too strong for anything to live right next to them, producing that bright and hot boiling effect, just to ensure they didn't get covered in life forms and algae blocking their light. You might extend long metal or ceramic tentacles or spurs off them for life to grab hold of, or let them migrate untouchably with things needing to swim along. Boiling and seething and bubbling around your world sea, these sea suns might just have bubbles of ecology roaming around with them if you left them to wander. Now, as we discussed last time in Super Earths, Between those and subsurface oceans of various icy moons and planets, we are not expecting to have any sort of shortage of natural oceans to use or terraform, and they should generally be easier to terraform than planet surfaces and atmospheres by and large. Additionally, I would expect most of humanity will want to build its habitats with lots of land and shallower seas and lakes, lots of beaches and reefs and sea bottoms you could scuba dive down to, though this assumes we have started building lots of megastructures before engaging in a lot of genetic tinkering and other transhuman paths, and that's a very debatable thing. So when it comes to megastructural habitat preferences, we will leave it at assuming tastes will vary. However, the purpose of megastructural habitats is to let you build far more worlds with far more living area than natural planets would ever supply, tailored to your wants and desires, so it lets you get away with using only a tiny fraction of your worlds for those which wouldn't be human paradise habitats, and still have billions of times Earth's living area devoted to weird worlds and habitats and nature preserves and more. Untold trillions of ocean habitats, big and small, Earth-like and unearthly, normal and alien. And as we saw today, we have no shortage of options for building space habitats with deep blue seas. Hoop walls and chain walls. We mentioned that an ocean habitat could be built in the shape of a hoop, but a hoop world is not merely a ring-shaped space station filled with water. It is an artificial planet shaped like an enormous torus, or less formally, a donut. Donut Planet lacks a certain dignity, so hoop world seems the better name. Strictly speaking, there are several kinds of torus, including spindle and horn varieties, where the central opening narrows or disappears. Our interest is in the ring torus, whose major radius, the distance from the center of the hole to the middle of the hoop, is much larger than the minor radius, or thickness of the hoop itself. That makes it easy to confuse with the Stanford torus, Banks orbital, or ring world, but the distinction is important. In those structures, people live on the inside of a rotating ring, and centrifugal force supplies nearly all their gravity. A hoop world contains enough mass to generate substantial natural gravity of its own, and people live across its exterior surface much as they would on an ordinary planet. It is possible, though extremely unlikely, that something vaguely like this could form naturally. A rapidly rotating planet might distort, break apart, and settle into a dense planetary ring. Or a close binary pair could conceivably evolve into some exotic toroidal arrangement. But this is megastructure engineering, so nature can go jump off a skyscraper. We are interested in building one deliberately. Left unsupported, a hoop world would not remain a hoop. Its own gravity would pull the mass inward until it collapsed into something more nearly spherical. To prevent that, we would use active support, probably on a planetary scale. Imagine immense orbital rings running through the structure, streams of matter racing around inside magnetic tracks at greater than orbital velocity, providing the momentum needed to keep the hoop expanded. Around those moving streams sits a mostly stationary sheath carrying the actual landscape, oceans, atmosphere, cities, and infrastructure. The underlying mass wants to collapse inward, while the fast-moving support system pushes outward, and the two are balanced against one another. In that sense, a hoop world resembles a planetary ring made solid, massive, and permanently stabilized. Saturn's rings are countless independent particles orbiting together, gradually spreading, colliding, and changing over astronomical timelines. A hoop world turns that general arrangement into one continuous, engineered planet. One possible construction route would be to reshape a gas giant, such as Uranus or Neptune. Their hydrogen and helium could supply most of the gravity-generating mass, while heavier material from the core or imported metals form this structural sheath. The moving conductive material inside the active support network might also be arranged to generate an immense magnetic field, protecting the atmosphere and inhabitants from radiation and solar storms. This gives hoop worlds a real advantage beyond spectacle. They could store enormous reserves of fusion fuel while providing many Earths worth of living area. Instead of leaving a gas giant as a mostly inaccessible ball of compressed atmosphere, we could reorganize its mass into a habitable world. A hoop world would also have many of the environmental features we associate with planets. Tilt its axis relative to the sun and it can have seasons. Different regions receive different amounts of sunlight, allowing tropical, temperate, and colder zones. Unlike a flat Earth, which tends toward broadly uniform illumination across each face, a hoop world offers a much richer range of climates. The geography would nevertheless be strange. The outer equator, the part of the hoop farthest from the center, would receive the strongest and most direct sunlight and might resemble a conventional tropical region. The inner equator, facing the central opening, would spend much more time shadowed by the opposite side of the hoop and would likely be cooler. Gravity would also vary. A hoop world would probably rotate once per day to provide a normal day-night cycle. On the inner equator, centrifugal acceleration from the rotation points in roughly the same direction as local gravity, making residence heavier. On the outer equator, centrifugal acceleration opposes part of the natural gravity, making residence lighter. Toward what we might loosely call the northern and southern arcs, since there are no poles, gravity strengthens again. This creates a planet divided not only into climate zones, but weight zones. One region might have Earth-like gravity, another noticeably lighter gravity, and another significantly heavier conditions. Plants, animals, architecture, and even human populations could adapt differently to each band. Nor does our hoop actually have to be circular, it could be more flat and elliptical, further altering the gravitational effect. Weather would be correspondingly complicated. The hoop's changing gravity, major temperature gradients, and strong Coriolis effects would drive currents unlike anything on Earth. The inner regions might be cold and stormy, while the outer equator held warm seas and tropical archipelagos. Yet with careful landscaping, like barrier mountains, atmospheric management, and a roughly 24-hour rotation, broad portions of the world could still approximate familiar terrestrial environments. The central opening creates opportunities of its own. Gravity is zero at the exact center, though that point is not naturally stable. A moon placed there could oscillate up and down through the hoop's opening, but would need active stabilization to keep perturbations from eventually sending it into the planet. Its motion would also be too slow to serve as a practical artificial sun, though it could provide moonlight and tides. A more useful option might be a stabilized central transportation hub. Because of the hoop world's immense radius and unusual gravity field, space elevators could extend inward from several parts of the surface toward that central port. 3 or more tether systems placed around the hoop could hold the hub in position while allowing rapid travel between distant regions. That matters because traveling around a hoop world by surface routes could take months. A central port would act as a planetary equivalent of an airport, train station, and orbital spaceport combined. A traveler could climb inward, cross the low-gravity central region, and descend toward another part of the world rather than journeying the long way around the surface. The hoop's interior also provides space for additional habitats. A long rotating cylinder or topopolis-like structure could run through the body of the hoop, creating an inhabited underworld beneath the outer surface. People there would live on the inner surface of the rotating habitat, upside down relative to the residents above. Carefully designed shafts could gradually accelerate travelers until they matched the rotation of the underground habitat before crossing through an airlock into its floor. With artificial lighting, that underworld could contain its own continents, forests, and seas. Additional concentric habitats could be nested below it, much as we add layers to a shell world. The visible planetary surface might therefore represent only a fraction of the hoop world's total living area. And once we are building actively supported planets of this scale, there is no need to stop at one. Multiple hoop worlds could pass through one another like links in a chain. Their center contains little gravity, providing room for neighboring hoops, while active supports and enormous atlas pillars could prevent the worlds from drifting together or colliding. Each link might possess its own climate, ecosystems, nations, and internal habitats. Extend that arrangement and we get a chain world, a sequence of artificial planets linked together and perhaps wrapped all the way around a star. Bridges, elevators, spacecraft corridors, and central ports could turn that chain into one connected civilization, a necklace of inhabited worlds encircling its sun. A hoop world takes the mass of a planet and bends it into a ring. A chain world turns those rings into links. But our next design goes larger still, abandoning planetary mass and building a single inhabited band broad enough to encircle the star itself. Ringworlds. The Ringworld is the great dream of megastructures, a ribbon the size of Earth's orbit, 300 million kilometers in radius, with a habitable inner surface offering more land than 1 million Earths combined. Stand on it and the horizon will curve not gently upward, but forever. A sky framed by mega mountain-sized walls holding the atmosphere, with rivers and continents sprawling for light minutes around the star. It's a breathtaking vision from the brilliant mind of the legendary Larry Niven, but also one that critics often dismiss as impossible. The usual objection is material strength. To spin at 1g rotational speeds, the rim must endure tangential velocities of over 1,000 km per second, and exert a tension on structural materials that no known material could survive, though the hypothetical material known as mag matter could. By conventional thinking, the stresses would tear it apart long before construction finished, and it would be spinning fast enough that its debris would actually be interstellar in its escape velocity. But as we've explored before, this problem is not insurmountable. The trick is to decouple the habitable band from the need to carry all that load itself. You don't build the Ringworld or the Banks Orbital out of one miraculous unbreakable material. Instead, you nest this ring inside a far more massive and slow rotating outer ring. This ring and the outer combined would have a net angular momentum equal to what all the mass would normally need to orbit that star, circumventing one of its support problems, but more importantly, it will push back against the other ring. That ring is pressing down hard on the outer ring below it, but they are not touching and are separated by vacuum. You can magnetically keep it pushed apart and distribute the load to both. This outer ring can be filled with some nice cheap mass like hydrogen and helium, and also serve as a protective shield for the inner ring. I should note that this is orders of magnitude easier with the Banks Orbital, and those do not have the issue of needing sun squares between the inner ring and the sun to block it out half the time for nighttime, or twilight bands for that matter. One neat thing about a Ringworld, and these also have their own dedicated episode, is that you can make a habitable Dyson sphere this way by having many rings, each a little wider or narrower than the last, so they don't quite touch, and tilted at an angle until the whole sun is englobed. Transport between these as a single habitat is also tricky but doable, offering you 2 billion times the total living area of Earth if done around our sun. This tends to be our upper limit on most megastructural conglomerations, as you need power to run life support on them, and the sun gives off 2 billion times the light that Earth needs, though it isn't a hard bar, and we'll get to ways around that today too. So while many will say a Ringworld is impossible, that's more a reflection of how daunting the scale is than a final verdict. With clever engineering and enough raw material to build entire planets into girders and stabilizers, it becomes less a fantasy and more a challenge. A Ringworld Dyson sphere would not be easy, but it remains a vision that fits within the laws of physics, provided we accept the structure as not a single ribbon, but a whole ecosystem of rings. That said, I think the Banks Orbital would be as big as anyone would go, simply because it's already dipping into the BWC megastructure range, where an equal amount of living space could be done more cheaply among many more smaller habitats. A BWC megastructure, incidentally, is short for because we can, and refers to those megastructures who exist mostly to prove you can build it if you wanted to, rather than any real practical reasons. A cube-shaped planet, for instance, is doable but kind of weird except for novelty. A giant disk world or flat Earth is actually a borderline BWC, as they do have some practical advantages over traditional worlds that might fit some niche applications. The Alderson Disc. Few megastructures are larger than the Ringworld, but there are some, and I thought we'd look at a couple before wrapping up today. Alderson Discs are among the largest and most visually striking artificial worlds ever proposed, an enormous flat disk encircling a star, with the star sitting in a hole at the center. In area, such a structure could rival a Dyson sphere, offering more than 1 billion Earths worth of surface. It also seems, at first glance, to provide one continuous world rather than countless separate shells. It's a popular design, too. The God Wheel of Malibu Comics is one, for instance, and designed by Larry Niven, who gave us so many megastructure concepts. Unfortunately, the basic design is spectacularly inconvenient. Sunlight arrives almost parallel to the disk's surface, so the star remains permanently on the horizon, and unlike a Dyson sphere, most of the light from the sun goes into space unused. The inner regions would be scorched by intense light and heat, while the illumination would rapidly dim and redden with distance. Farther outward, the surface would fade through perpetual twilight into frozen darkness. Left alone, only a relatively narrow band would receive remotely comfortable conditions. The disk would also require an immense wall around its central opening. Without one, air and water would tend to migrate inward and eventually spill into the star. Gravity would not point neatly downward across the entire surface either. Near the center, it would be mostly perpendicular to the disk, but farther outward it would increasingly pull toward the middle. Oceans and atmosphere would accumulate in the inner regions, while inhabitants close to the rim would feel as though the ground were steadily tilting beneath them. Though, as we discussed, we could get around it with some non-homogeneous mass distributions and giant mountain ranges and some active pumping. and the structure itself would not naturally remain flat. Its gravity would pull the disk inward, encouraging it to contract, buckle, and ultimately collapse toward a more spherical shape, one with a star at its center. No passive material we know could withstand the stresses involved. These problems are severe, but they are not necessarily fatal, and the designer, the late Dan Alderson of NASA JPL, would have been aware of them. We have some crazy megastructures that made no physical or engineering sense from designers who had no background in either, and this is not the case here, even if it pushes the boundaries. Active support structures could hold the disk apart. Concentric orbital rings carrying streams of rapidly moving matter could provide the momentum needed to prevent collapse. Each ring could be denser than the one inside it, helping compensate for the inward pull of the disk's mass and producing a more uniform surface gravity. Atlas pillars or space fountains could support the outer skin and move material toward the structure. The disk's interior could be filled largely with hydrogen and helium. Those elements are abundant, and while they are poor building materials for an Earth-like planet, they work perfectly well as bulk mass for generating gravity. Since the disk would be enormously wider than it was thick, even a structure tens of thousands of kilometers deep would still remain comparatively thin. Lighting is surprisingly easier to fix. Vast steadite mirrors could hover above and below the central star, supported by radiation pressure rather than conventional orbits. By curving, angling, rotating, or selectively shading those mirrors, engineers could redirect sunlight downward across the disk. They could create illuminated bands, moving day and night, seasonal cycles, and warmer or colder regions far from the star. So too, rather than placing a giant star at the center, where its mass is going to pull things inward, we could actually take several other stars and orbit them around the Alderson Disc's outer edge, using the mirrors again to reflect their light back in, and the quantities, timing, and patterns that we wished. This lets us transform the Alderson Disc from a sunburned inner ring surrounded by frozen gloom into a deliberately landscaped artificial world with Earth-like conditions and abundant power to run its active support systems. Circular mountain ranges and retaining walls could further control air and oceans, while the rim and central wall could serve as power collectors, transport routes, or radiators. The harder question is not whether an Alderson Disc can be built, but why anyone would bother. This is not simply a flat planet or cube world built for novelty among trillions of more efficient halves. It is a K2 scale because we can megastructure. It uses matter less efficiently than a shell world or a swarm of rotating habitats, and introduces problems those designs avoid. Its great advantage is continuity, one immense connected surface of land and sea, extending across the entire star system, without requiring spacecraft to travel between habitats. It is not the practical choice. But civilizations capable of dismantling planets and engineering stars may not always choose the practical option. Sometimes they may want one world broad enough to hold an entire solar civilization beneath a single sky. And in a galaxy of billions of systems, it seems plausible a Kardashev 3 civilization might decide to build a few of these just because they can.
Black holes are amongst the most dangerous and destructive things in the universe, so let's go live on one. So today, we return to the Outward Bound series to look at colonizing black holes. We talk fairly often on this channel about advanced civilizations using black holes in various ways, but we're usually talking either about artificial micro-black holes that emit Hawking radiation and need to be fed constantly so they don't disappear, or about civilizations so far forward in time that black holes would be prevalent, while what we call stars would be ancient history, part of a brief, bright era when the universe was still settling down from the Big Bang. But today, we are going to talk about how and why black holes might become the preferred place for much nearer future civilizations to colonize, even while stars still burn and uninhabited planets are abundant. In a lot of science fiction, a ship stumbling across a black hole is cause for panic, but in reality, the crew would probably be popping the corks on the champagne because that's some very valuable real estate they just found. To understand why, let's talk briefly about what our descendants would be looking for in a place to colonize. Stars are useful fundamentally as power sources. Earth is basically self-sufficient except for the light we receive from the sun, which keeps our planet comfortably warm and powers our entire ecosystem. But that power doesn't originate on the surface of the sun that we can see. That goes on deep down inside, where fusion turns hydrogen into helium and produces lots of lethal gamma rays. They get absorbed and re-radiated as lower energy, longer wavelength photons many times by the layers above, until that energy is eventually emitted at the surface, mostly as visible light and infrared in the case of our sun. Many of our colonization methods rely on collecting that light, and we discuss lots of ways to concentrate or diffuse that light to let us settle at distances of our choosing from the star. Other colonization plans involve replicating sunlight in our habitats using other energy sources. Fusing hydrogen into helium produces millions of times more energy than any chemical process does, but controlled, contained fusion is still something that eludes us. We do achieve fusion in hydrogen bombs, which are often compared to the sun, but current hydrogen bombs require rare isotopes like deuterium, tritium, or lithium deuteride, the ones that are easiest to fuse. So a nice reactor you can dump common hydrogen into and get electricity from is quite a ways off, and it would still only release less than 1% of the energy available in matter, Einstein's E equals mc squared. Black holes are much easier and efficient. There are several ways to get power from a black hole, and which one you'd use depends on your level of technology and the size of the black hole. You can check out our video about black hole ships from a few weeks back if you'd like to learn more about those methods. But for black holes of the size we are discussing today, the size you would colonize, the easiest method is to simply drop matter in and collect the X-ray radiation pouring from the accretion disk. Matter in the accretion disk is compressed with such force and moving so fast that friction produces immense heat, which for an average natural-sized black hole would be radiated in the X-ray part of the spectrum. This is what we believe powers quasars, so a scaled-down version of the brightest objects in the universe would be the power plant of your colony. Black holes also have potentially enormous value for industrial uses, besides just being a great power source. They are the perfect way to dispose of anything you don't feel is safe or economical to recycle or otherwise safely dispose of, as a black hole doesn't care what kind of matter you feed it, just the amount. People often talk about dumping radioactive waste into the sun, which is not a great idea for reasons we'll save for another day. But in a black hole's case, it's actually a highly profitable way to dispose of dangerous material. As we discussed in black hole ships a few weeks back, these objects are also handy for space travelers because they allow you to change directions with minimum fuel. You can fly close to any massive body to alter your course or give yourself a little speed boost, but the sharper the turn you want to make, the closer the pass you'll have to make, which might be too close to the heat of a star, if not inside the star itself. And contrary to what's depicted in most sci-fi, you can fly closer to a black hole than you can to a star of equal mass, because it's much cooler and doesn't have all that pesky stellar atmosphere and solar wind that you'd rather not encounter at high speed. Though I'll note that black holes are not the only dead stars handy for space travel. When a star starts dying, it usually spends a fair amount of time as a red giant, and those are actually so thin you could run a ship through their atmosphere as a means of slowing down. Not our topic for today, but since slowing a ship down is one of the biggest issues with interstellar travel, these offer a partial solution. You can push on ships with lasers to accelerate them, but there will be no laser to slow you back down at an undeveloped destination, so that constrains how fast you can travel to uncolonized systems. Any fuel you have to save for deceleration at the end can't be used for acceleration along the way. Red giants might be ideal vanguard systems for colonization because you can reach them at higher speeds than other neighboring systems, letting you set up as the first port of call for that region of the galaxy. In this same way, black holes make good waypoints for distant places, as you can head in their direction and use them to alter your course and boost your speed, and they can also be used to slow down too. Indeed, one you can see a long way off is likely jetting relativistic matter off its poles, and you might be able to use conventional sails or magnetic sails to use that for braking drag or an added boost. So such places might naturally tend to be the first distant places we visit and settle, and once you've colonized it, assuming you've got some raw materials nearby, which is quite likely as even the supernova that produced it wouldn't have been powerful enough to destroy the original outer planets it probably had, you've got a giant power plant on hand and raw materials to feed it and build with. Initially, you wouldn't want to live too close, though again, not for fear of gravity. The method you're likely to use for power generation is to throw matter around a black hole to form an accretion disk, which emits huge amounts of X-ray radiation. So if you want to be close, you'll have to wrap that thing in radiation shielding, and to prevent any large chunks of matter falling in and producing big blasts of X-rays. Of course, if you're building a shield, you might want to throw some dirt on top of it. Dirt's good radiation shielding too, and we can add air and water and artificial lighting, and presto, new planet. Except it's kind of a huge one. Your typical stellar mass black hole is 1 million or more times as massive as Earth, so if you build a shell around it for normal Earth gravity, it would be a shell 1,000 times wider than Earth and 1 million times larger in surface area, a true mega-Earth. I should note it would also have an escape velocity 32 times higher than Earth's, 354 kilometers per second, instead of 11.2 kilometers per second. The gravity well is bigger and deeper, for all that the force on you is the same as on the surface of Earth. Easy to visit, but hard to leave, making it quite the tourist trap. Now the means for doing this shell is one we've discussed many times on this channel, and that's the orbital ring. Our episode on colonizing the Sun gives a full discussion of how to do that around a massive object, but basically, by creating a hollow loop of matter that does not orbit the planet or star or black hole beneath it, but merely wraps around it, then spinning another hoop or stream of matter inside it at faster than normal orbital speed, we get a big stationary ring we could walk around on. We could make many of them, cocooning that object with a mesh, and then presto, shell world. In this case, you'd probably have a lower shell from which to dump matter into the black hole and absorb the radiation to make power. You might have several habitable upper layers too. Such planets had to be very big because black holes are as massive as large stars, and since gravity increases with mass and falls off with distance, and you have to be a lot farther from a black hole than from Earth's center for the gravity to be walkable. As mentioned, black holes often gain mass or even merge with other black holes, as we often find black hole candidate stars, supergiants, growing up together in big clusters. So there are going to be some very large ones of hundreds or even thousands of solar masses. Shells around them work just fine too, but they get even harder to leave. Even though the gravity on that shell is presumably the same as Earth's surface, the escape velocity will keep rising. As you probably know, time slows down in bigger gravity wells, and this slowing can be approximated as the same as the escape velocity in terms of the classic special relativity effect of time slowing on a fast spaceship, at least when you're not too close to the event horizon. So a shell that had an escape velocity of 1% of light speed has the time running slow on it basically the same as a spaceship traveling at that speed, which in truth is very little. Your clock would only lose about 4 seconds a day, or about 26 minutes a year, and would require a mass of several thousand solar masses. Such black holes are not very common, though considerably larger ones reside at the cores of most galaxies. On our first example, the simple mega-Earth built around a black hole of a few solar masses, with an escape velocity of merely 354 kilometers per second, time would only be running about 22 seconds slow per year.
Birch Planets, the final no-FTL civilization. We can go far beyond modest megaplans around stellar mass black holes, and if we do, we arrive at perhaps the most extreme megastructure ever conceived, the Birch Planet. Originally proposed by the late great engineer and physicist Paul Birch, who also gave us the orbital ring and methods for terraforming Venus, this idea envisions not just building around a black hole, but using its gravity to support entire layers of civilization stacked atop one another. A typical Birch Planet would be constructed around a supermassive black hole, like the one at the heart of the Milky Way. That object has a mass of 4.5 million suns, or about 1.5 trillion Earths. That means a single spherical shell around it, at the radius where gravity equals Earth's surface gravity, has 1.5 trillion times the surface area of Earth. Living area of the same gravity on a spherical shell rises linearly with mass, and unlike a Dyson sphere, which must sit millions of kilometers from a luminous burning star, a Birch Planet could have dozens, hundreds, or even thousands of these shells layered atop one another. They may be able to get around the normal waste heat issue of multi-layer shell worlds too, as dumping infrared waste heat into a black hole by reflecting it might get around the normal thermodynamic restrictions. Each shell represents another Earth-like surface, times a trillion, supported by active structures and powered by the gravity of the black hole itself. This scale produces living space beyond imagination, and contiguous too. Even the shell layers can be connected by spiraling landscapes, allowing you to walk, swim, or fly between every piece of it. A mere dozen layers would offer the surface area of 20 trillion Earths. 1,000 layers? That's a Kardashev Type 3 civilization's worth of living room, all within a light hour's commute. Unlike a sprawling galactic empire, it's intensely concentrated. Even in its most extreme form, a black hole of 1.55 trillion solar masses, potentially including dark matter, with surface gravity equal to Earth's, you are still talking about a structure just 1 light year wide. Each shell provides a living area of 516 quadrillion Earths, and as you move outward, that only increases. Though gravity diminishes with distance, at this scale, even layers spaced hundreds of millions of miles apart would experience only trivial differences in surface gravity. That's how vast a maximum scale Birch Planet truly is. Information can cross the entire construct in under a year, enabling real-time governance, trade, and cultural cohesion for a civilization potentially housing billions of billions of billions of people. No light lag between systems, no fragmentation around the stars, a unified super-civilization in a single titanic construct, outnumbering us a quintillion to 1. Time dilation adds another benefit. Near the lower layers, time slows drastically. A resident of Layer 10 could visit Layer 1000 and return to find the calendar above barely moved, making Birch Planets ideal for long-term planning, computation, or shelter from cosmic threats. The deepest levels might function as temporal bunkers, safe from both entropy and external upheaval. I cannot even imagine what it would take to invade such a place, and destroying it would serve no sane purpose, and likely be nigh impossible too. Again, there is a natural upper limit to Birch Planets. A black hole with 500 quadrillion times Earth's mass has an event horizon 1 light year in diameter, with surface gravity equal to Earth's. Beyond that size, any shell would lie inside the event horizon and cease to be usable. Indeed, with frame dragging concerns, you might need to stay even lower mass, though your black hole does not need to be rotating to cause frame drag, except this is part of how we generate power off of one. This sets a hard boundary on how big such a structure can get under known physics, an ultimate capstone on megastructure engineering of a single Earth-like superplanet. While vast in scope, this upper limit also implies a kind of closure. A civilization that builds such a structure has likely harvested its entire galaxy, even some neighbors, and has nowhere else left to expand. It is not just the most massive habitat possible, it's the final, complete expression of a civilization's turn inward, seeking unity, permanence, and control in a universe otherwise racing toward entropy. And that's the other function of a Birch Planet. Much like artificially compactified galaxies, it solves the divergence problem. In a normal Kardashev 3 empire, it might take millions of years to settle a galaxy, and the colonies on the opposite ends might be more alien to each other than we are to trilobites. But by compressing the civilization to one location, communication stays practical, identity remains intact. You have a single empire, not a million echoing fragments of a long-dead species. Not that it's likely to be super uniform, given that Earth is not. It may have countless nations on it, but some degree of meaningful uniformity is possible, and for baseline humanity too. We do not have to limit ourselves to only contemplating massive megamines using stars as their engines that are part of some galactic civilization of a few 100 billion M-brains. It's also a near-perfect hiding place. Birch planets are not covert in construction. Gathering and reshaping entire galaxies worth of matter is not subtle, but once complete, they are easy to miss. All the heat and light is redshifted by proximity to the event horizon. Their waste heat might be dumped into the black hole entirely. Their size, while vast, is tiny compared to a whole galaxy. If you're not looking directly at one, you would miss it, and if you are on one, there's little reason to look out. You've already harvested the universe. The outside is just noise. Birch planets are not exactly stealthy if you're trying to hide from parallel civilizations, but they could still be out there, floating in the apparent emptiness where a galaxy used to be, and we might easily miss them. Normally a K3 or near K4 civilization, loud, grabby aliens, would be impossible to overlook, even from a billion light years away with modern astronomical instruments. But a Birch planet concentrates its emissions, redshifts its light, and may even dump its waste heat into a black hole, or most of it. It doesn't need to be silent, just hard to notice, and if it took 1,000,000 years to go from us, now, to building one, that's a fairly short time in universe terms. Even if it were happening to every galaxy, only 1 in 1,000 would be visible in the process of building one, at most, so easy to miss, at least for us. Whether for power, population, unity, or obscurity, the Birch planet represents a natural terminus for galactic ambition, not an empire among the stars, but a single staggering construct that is the empire, compressed into a globe of quiet infinity, not just the final step of infrastructure, but perhaps the last word in civilization itself. It is also something that could be built without a human or human-level intelligence ever leaving your homeworld or home system. There's nothing ultra-complicated about grabbing resources, or even moving stars, that even modern AI could not do. This idea fits neatly with the concept of an interdiction bubble civilization, or IBC, a civilization that believes its distant interstellar colonies will inevitably diverge to the point of becoming alien and possibly hostile. Seeing little long-term profit from trade or shared research beyond its immediate stellar neighborhood, perhaps a radius of only a few light years, it adopts a strategy of containment and control. It strip mines surrounding systems, rendering them incapable of supporting potential rivals, and turns itself into a kind of fortress oasis. The harvested resources are brought home, while the surrounding region is left a barren desert, intentionally emptied of anything that could threaten the core. In this case, they probably start by building a Matryoshka shell world around their original home planet and just keep adding layers, until the planet becomes geocentric, with the sun and its Dyson swarm effectively orbiting it. Over time, they continue expanding, replacing older inner layers with material brought in from gas giants, and eventually centering the entire structure around an artificial black hole. All the hydrogen and helium they collect gets fed into the black hole, while rocky material is used to build new layers around it. Stars can be disassembled through star lifting, see our episode on that topic, and your Birch planet or compact artificial red dwarf galaxy does not need to be centered on your natural galactic core. You can simply keep expanding your homeworld, evolving that initial Dyson swarm into a Birch planet or a cold cluster, then into an artificial galaxy, and all the while, robotic systems can be quietly harvesting the rest of the universe to bring home. The worlds we choose. A Birch planet is close to the greatest concentration of living space we can imagine without faster-than-light travel. An artificial world wrapped around a supermassive black hole, large enough to contain civilizations beyond counting, yet still governed by the same gravity, heat, pressure, and material limits we discussed throughout this episode. It seems a fitting place to end, because today we have traveled from worlds small enough to circle in a day to worlds so vast that crossing them might take longer than civilizations endure. We've shaped planets into cubes, discs, bowls, hoops, and sombreros. We've enclosed worlds beneath artificial skies, hollowed them out to create new layers, floated cities through alien atmospheres, constructed oceans in empty space, and built artificial suns whenever nature placed the real ones somewhere inconvenient. Yet beneath all those strange geometries, the central idea has remained remarkably simple. Planets are places nature gives us. Habitats are places we choose to make. That does not mean natural planets will become obsolete. Earth will always be humanity's first home, while Mars, Venus, Titan, the Moon, and countless planets and moons orbiting other stars may become homes in their own right. We may terraform some, bioform ourselves for others, and preserve many untouched as wilderness, scientific reserves, or simply places whose beauty does not require our improvement. But natural planets are only one possible kind of home. Once a civilization can move matter on planetary scales, gravity becomes architecture, atmospheres become plumbing, climate becomes environmental control, geography stops being an accident inherited from geology and becomes something that can be planned, expanded, revised, or rebuilt. The future may still contain mountains, forests, rivers, farms, towns, coastlines, and open skies. It may simply contain far more of them than nature ever supplied, and in arrangements nature would never have attempted. Most people probably will not live on the extreme structures we examine today. They are more likely to inhabit the cylinders, toruses, spheres, clustered settlements, and other comparatively practical designs explored in our first Space Habitats Compendium. That episode forms the other half of this tour, focusing on the habitats we could build sooner, more easily, and in far greater numbers. So if you began here, that first compendium is the natural place to continue. Together, these two episodes carry us from the earliest rotating settlements to artificial worlds capable of housing entire galactic civilizations. But even together, they do not cover everything. After more than 1,000 videos, live streams, collaborations, and bonus episodes, we've explored an enormous range of futures, and many of the subjects discussed today have full episodes of their own. Others have been heavily abridged, while many habitat concepts could not be included at all. We also have many other compendiums gathering years of discussion into broader tours of major subjects, from megastructures and terraforming to interstellar travel and possible futures of civilization. They offer a way to explore the channel's growing library without needing to begin more than 1,000 episodes ago, though the option is certainly there for anyone feeling particularly ambitious. And there is still far more to explore. There are older topics deserving complete remakes, designs that have never received a dedicated episode, and ideas that may not have occurred to anyone. That is one reason these compendiums are valuable. They let us collect ideas scattered across years of the channel, update them, compare them directly, and discover connections that were less obvious when each subject stood alone. But even 5 hours can only provide a map of territory this large. It cannot explore every valley, ocean, cavern, city, and artificial sky. So let us know which structure most deserves a deeper episode of its own, and, more importantly, which one you would actually choose to call home. Would you prefer a private microplanet, a continuous world encircling a star, a Birch Planet whose surface could hold whole civilizations beyond counting? There may be no single right answer, and that is one of the greatest promises of space settlement. The purpose is not to replace one planet with another standard design, it is to create more choices, more environments, more experiments, more cultures, and more ways of living than any single world could ever contain. A civilization spread among artificial worlds need not agree on ideal climate, gravity, landscape, architecture, government, or even body type. It can build different answers and place enough distance between them that those answers need not compete for the same patch of ground. Space does not merely offer civilization more territory, it gives us the opportunity to reconsider what territory is. If you have remained with us through all 5 hours of this journey, thank you. Your time and attention are not small gifts, especially for an episode this enormous. I hope the voyage has been worth taking. Projects like this require a great deal of writing, research, editing, artwork, animation, and production. They are possible because viewers choose to support this channel directly. Patreon support helps us create new episodes, revisit older subjects with improved science and production, and assemble projects like this for more than a decade of work. So, if you'd like to help us continue producing these long-form explorations, and in return for deeper looks at many of the subjects we don't touch upon today, you can support the show on Patreon through the link in the episode description. And to everyone already supporting us there who has helped this channel in any other way over the years, thank you. You've allowed us to keep exploring ideas that are too large, too strange, or simply too detailed for most formats, and occasionally too large even for 5-hour episodes. We began by asking whether planets might someday be among the smallest worlds civilization inhabits. Perhaps the deeper answer is the size was never the most important difference. A planet is a world we are born upon, An artificial world is a future we decide to build. And somewhere in that distant future, be it an engineered sun or beside an ocean suspended in space, people may look across the landscape that never existed in nature and regard it as we regard Earth today, not as a megastructure, an engineering project, or a triumph over physics, but simply as home. As always, thanks for watching, and have a great week.